Hello there and welcome to Physics with William, where we take the familiar objects sitting quietly around us and give them just enough attention to reveal the physics they have been hiding all along. Tonight, we are looking at something so ordinary that you may have used it several times already without thinking about what was happening inside it. A battery. Perhaps there is one in the phone beside you, another in a laptop somewhere nearby, a few more inside wireless headphones, a watch, a toothbrush, a remote control, or one of those portable chargers that always seems fully charged until the exact moment you actually need it. Batteries have become so normal that we tend to think of them only in terms of a little icon on a screen. Full is good, empty is inconvenient. Somewhere in between we begin searching for a cable, but there is a strange fact hidden behind that familiar routine. A fully charged battery weighs slightly more than the same battery when it is discharged. The difference is far too small for your hand to feel, and far too small for an ordinary scale to notice. But according to physics, it is there. When energy is stored inside the battery, the total mass of the battery increases. When that energy leaves, the mass decreases again. Nothing dramatic happens to the shape of the battery. It does not swell with some invisible electrical substance. It does not collect a large pile of extra particles. Yet when it is full of usable energy, it is also, in the strictest physical sense, a little bit heavier. Before we go further, I would love to know where you're listening from tonight and what rechargeable device is closest to you right now. Maybe your phone is resting on the bedside table with plenty of charge left. Maybe it is connected to a cable and quietly climbing toward full while you listen. Perhaps your laptop is plugged in across the room, or your headphones are sitting in their case gathering enough energy for tomorrow. Wherever you are, there is a good chance that something nearby is gaining a tiny amount of mass as electricity moves into it. It is such a small change that nothing in your daily life depends on noticing it, but that is part of what makes it interesting. Physics often hides its best surprises in places where our senses are simply not sensitive enough to catch them. If you find these slow journeys through everyday science relaxing or interesting, you can leave a like and subscribe to the channel. It helps more people find this quiet little corner where batteries, clocks, light, gravity, and all the other ordinary pieces of the universe are allowed to become slightly less ordinary. For now, get comfortable and consider the battery nearest to you. It may look exactly the same whether it is charged or empty, but inside, its physical condition can be very different. The easiest way to see why this question is surprising is to think about how we normally make things heavier. If you place a book into a bag, the bag gets heavier because you added matter. If you pour water into a bottle, the bottle gets heavier because more material is now inside. If you put another potato on a kitchen scale, the number goes up for reasons that require very little theoretical physics and perhaps slightly more concern about why you're weighing so many potatoes. In everyday life, more weight usually means more stuff. That intuition works so well that we carry it into situations where it is no longer complete. Charging a battery does not look like adding stuff. You can place a rechargeable battery on a table, charge it, disconnect it, and look at it afterward. It still has the same casing, the same shape, the same components, and essentially the same collection of atoms. Nothing obvious has been added, yet the charged battery contains more energy than the discharged battery, and the extra stored energy contributes to the mass of the entire system. Imagine an impossibly sensitive scale, much more precise than anything you would keep in a kitchen, a workshop, or even most laboratories. Place a discharged battery on it and record the mass. Then connect the battery to a charger without otherwise disturbing the setup. As charging begins, electrical energy enters the battery. The chemical state inside starts to change. Charged particles move through the internal materials. Electrons are driven through the external circuit. The battery gradually moves away from the condition it naturally settles into when discharged, and toward a condition where energy has been stored and can later be released. If our imaginary scale were perfect, the reading would rise by a very small amount as that process continued. When the battery reached its charged state, it would have more mass than it had at the start. If you then use the battery to power a device, the stored energy would gradually leave. The device might turn that energy into light from a screen, sound from a speaker, radio signals from an antenna, movement in a motor, and eventually heat that spreads into the surrounding air. As the energy left the battery, that tiny extra contribution to its mass would leave with it. This is where everyday language can make things more confusing than they need to be. We often say that a battery is full, and the word full suggests a container. A glass can be full of water, a cupboard can be full of biscuits, a train can be full of passengers. If a battery is full, it is natural to imagine that something must have been poured or packed into it. Electricity, perhaps. Maybe charging pushes electrons inside until there are enough of them waiting around to power the device later. It sounds reasonable, and it is also not quite what happens. A rechargeable battery does not work like a bucket collecting electricity. It stores energy by changing the arrangement and chemical condition of the materials that are already there. Electrons certainly matter, and they move during charging and discharging, but the story is not simply that a charged battery has been stuffed with a large number of extra electrons. The battery as a whole remains very close to electrically neutral. What changes most importantly is the energetic arrangement of its internal components. A useful comparison is a spring. Imagine an ordinary metal spring sitting in a relaxed state. Now compress it. You have done work on the spring, and it can now release that energy if you allow it to expand again. The spring has not gained a meaningful collection of new atoms. It is made from the same metal before and after compression. What has changed is its physical state. The atoms and bonds are arranged in a way that stores energy. If you release the spring, that energy can become motion, sound, heat, or perhaps the sudden departure of a small object you should not have placed in front of it. A battery is much more complicated than a spring, but the broad idea is similar. Charging pushes the internal system into a state with more stored energy. The battery can later move toward a lower energy state, and in doing so, it can deliver energy through an electrical circuit. There is another simple example in something even more familiar. Take an object and warm it. A warm object contains more internal energy than the same object when it is cooler. The atoms and molecules inside are moving and vibrating differently. The warmer object also has slightly more mass. Again, the difference is extremely small, and you will not settle any household argument by putting hot and cold cups of tea on a bathroom scale. The scale will have far more trouble with air currents, evaporation, vibration, and its own limitations than it will ever have detecting the change caused by the extra thermal energy. But the physical principle remains. If a system contains more total energy, then its mass is greater than it would be with less energy. The battery is another version of that idea, except the extra energy is stored mainly in the electrochemical state of the cell, rather than simply as heat. This is one of those places where our ordinary picture of matter and energy begins to blur. In daily life, matter feels like the solid part of reality. It is the phone in your hand, the chair beneath you, the cup on the table, and the floor that you would prefer to remain exactly where it is. Energy seems less substantial. We speak of it as something objects have. Use, gain, or lose. A moving object has energy. A hot object has energy. A battery stores energy. A beam of light carries energy. It can be tempting to think that mass belongs to material things, while energy is simply an activity taking place around them. Modern physics does not draw such a sharp boundary. The total energy contained in a physical system contributes to the mass of that system. Change the energy, and you change the mass. That does not mean the change is usually large. In fact, for ordinary amounts of energy, the corresponding change in mass is almost absurdly small. A phone battery can store enough energy to keep a device running for many hours. That energy can illuminate millions of pixels, run processors performing huge numbers of operations, communicate with distant antennas, track location, play music, show video, and maintain a determined collection of background processes that seem deeply committed to using the remaining charge. From our point of view, that is a useful amount of energy. From the point of view of mass, however, it is tiny. The amount by which the battery becomes heavier is so small that you would never notice it while holding the phone. Your hand is not remotely sensitive enough. Ordinary scales are not remotely sensitive enough. Even extremely precise measurements would have to deal with other effects that are much larger than the change we are trying to detect. Temperature alone creates trouble. Batteries often warm slightly while charging. A warmer battery can heat the air around it, creating small currents that affect a sensitive balance. Materials expand with temperature. The surface of the battery can interact differently with moisture in the air. The cable used to charge it can pull or twist with forces far larger than the mass change associated with stored energy. Vibrations from footsteps, traffic, ventilation systems, or the building itself can overwhelm the effect. The scale can drift. The battery chemistry can change in tiny ways unrelated to the ideal energy storage process. At the level where this mass difference lives, the ordinary world is surprisingly noisy. The fact that the effect is hard to measure does not make it uncertain. This is an important distinction in physics. Some things are difficult to observe because we do not know whether they happen. Other things are difficult to observe because we know the effect is extremely small compared with everything else going on. The mass difference between a charged and discharged battery belongs to the second category. The principle is well established. The practical challenge is separating that tiny change from a much larger collection of mundane disturbances. It is rather like trying to hear a quiet whisper while someone nearby is vacuuming the carpet. The whisper may be perfectly real, but you have chosen an unfortunate moment to measure it. You might reasonably ask where the extra mass comes from. If the battery becomes heavier as it charges, has new mass somehow appeared? No. The battery gained energy from somewhere outside itself. That energy was carried into the battery through the charging process. Perhaps the electricity came from the grid. Perhaps that electrical energy ultimately came from sunlight, wind, moving water, nuclear fuel, natural gas, or some mixture of sources. The charger transfers energy into the battery and changes its internal state. When the battery gains energy, it gains the corresponding tiny amount of mass. Somewhere else, energy has been lost or transformed. If we include the entire system rather than focusing only on the battery, nothing has been created from nothing. Imagine charging one device from another. A portable power bank is connected to a phone. The phone battery gains stored energy and therefore gains a tiny amount of mass. The power bank loses stored energy and therefore loses a tiny amount of mass. In an ideal transfer with no losses, the energy removed from one would equal the energy added to the other. Real charging is not ideal. Some of the energy becomes heat in the batteries, cable, electronics and surrounding environment. The total accounting still works, but now you have to include that thermal energy as well. If the cable feels warm, some of the energy has simply taken a route that is less useful for charging the phone and more useful for making the cable slightly warmer than the table. There is a subtle point here that makes the battery especially interesting. The extra energy is not best imagined as belonging to one individual particle. You cannot open a charged battery, point to a particular electron, and confidently announce that this one is carrying the energy needed to send tomorrow morning's first message. The stored energy belongs to the configuration of the system. It depends on how particles are arranged, where ions are located, how electrons are distributed, what chemical states are available, and how the different parts interact. A battery is not just a pile of ingredients. The relationships between those ingredients matter. Think about a bookshelf. You could place the same books on the floor or arrange them on shelves. The total collection of books has not changed, but the arrangement has. In one case, the books are lower. In another, some of them have been lifted and now have more stored gravitational energy because of their position. If a book falls from the shelf, that stored energy can become motion, and then sound, heat, and perhaps embarrassment if you were the person who stacked it badly. Nothing about the book's identity had to change for the energy of the arrangement to change. In a battery, the relevant interactions are electrochemical rather than simply gravitational, but again the arrangement matters. When a rechargeable battery is charged, the external power source drives processes that would not continue indefinitely on their own. It pushes the internal materials into a state from which they can later release energy. This is why charging requires a source of energy in the first place. You're not merely waiting for the battery to decide that it feels more energetic. The charger forces a change. The battery stores the result of that change in its internal chemical condition. Later, when you connect the battery to a device, the system can move back toward a lower energy state while transferring energy through the circuit. This also helps explain why the phrase empty battery is not literally correct. A discharged battery is not empty in the ordinary sense. It still contains matter. It still contains enormous amounts of internal energy associated with the atoms and particles from which it is made. It still has chemical structure. It may even retain some usable energy depending on what we mean by discharged. The word empty simply means that the battery is no longer in a state from which the device can conveniently extract the expected amount of electrical energy. The battery has not become a hollow shell. It has moved toward a lower energy configuration. The same is true at the other end. A full battery is not full of electricity in the way a tank is full of fuel. The battery materials have been rearranged into a more energetic state. The difference sounds small, but it changes the mental picture completely. Fuel tanks become heavier, mainly because additional fuel is physically added. Rechargeable batteries become heavier mainly because energy is transferred into the same system and stored through changes in its internal state. This distinction becomes even clearer if we imagine a sealed battery that never exchanges material with its surroundings. No atoms are allowed to enter or leave. We charge it through an idealized process that transfers only energy. The battery still becomes more massive. That thought experiment tells us that the mass increase cannot require extra matter crossing the boundary. Energy alone is enough to change the total mass of the system. Once that idea settles in, several other strange consequences begin to look less strange. A wound mechanical clock has slightly more mass than the same clock after it has run down. A compressed spring has slightly more mass than the same spring after it relaxes. A hot sealed container has slightly more mass than the same container after it cools, assuming the released energy has escaped from the system. A charged capacitor has more mass than the same capacitor after it is discharged. These are not separate tricks. They are different examples of the same principle. The battery simply gives us a particularly convenient way to encounter it, because we charge and discharge batteries constantly. Every time your phone moves from low charge to high charge, its mass changes. Every time your laptop battery slowly drains during a long afternoon, its mass decreases by an amount so small that your desk remains unimpressed. Every time a power bank transfers energy into another device, mass is being redistributed along with that energy. The numbers are tiny, but the principle reaches all the way into the foundations of modern physics. What makes the subject even more interesting is that the mass difference is not explained merely by saying that energy has mass and stopping there. To understand why the charged state contains more energy, we need to look at what the battery is actually doing internally. We need to follow the movement of electrons through the external circuit, the movement of ions inside the cell, and the chemical changes that allow the battery to store energy without simply becoming an electrically charged lump. That internal process is where the familiar battery icon on your screen connects with the less familiar world of chemistry, electric forces, and the energy of physical arrangements. So picture the battery beside you once more. From the outside, it appears calm. There are no moving gears, no visible fuel, no tiny piston announcing that useful work is being prepared. Yet while it charges, particles inside are being driven into different positions and chemical states. The system is being prepared to release energy later. The small increase in mass is a consequence of that stored energy, but the real story begins with the rearrangement that makes storage possible at all. To see how that happens, we have to move past the battery percentage on the screen and look at what is actually changing inside the cell while the charger is connected. To see what is actually changing inside a battery while it charges, it helps to forget the little battery icon on a screen for a moment and imagine the cell as a carefully organised chemical system with two main regions separated by a material that allows some particles to pass while blocking others. In a typical rechargeable lithium-ion battery, one side is called the anode, and the other is called the cathode, with an electrolyte between them that allows lithium ions to move. The exact materials vary from one battery design to another, but the basic job remains similar. During charging, an outside source of electrical energy forces the battery into a condition that it would not naturally remain in if left alone. The charger is not filling an empty space, it is pushing particles into a different arrangement and changing where energy is stored within the chemical structure. That new arrangement is less relaxed than the discharged one, which is precisely why the battery can later release energy and power something useful. The first thing to notice is that two kinds of motion are happening at once. Electrons move through the external electrical circuit, while ions move through the inside of the battery. Those two movements are connected, but they do not take the same path. Electrons cannot simply travel straight through the electrolyte from one side to the other. Instead, during charging, the charger drives them through wires and electronic components toward one electrode. At the same time, lithium ions move through the electrolyte inside the battery toward that same general side. The battery therefore keeps its electrical balance while its internal arrangement changes. This is one reason the idea of a battery being filled with electrons is misleading. The electrons are part of the process, but the battery does not simply accumulate a giant excess of them. If it tried, electric forces would quickly become enormous, and the whole arrangement would be far less convenient than the neat rechargeable device sitting beside you. Imagine a theatre after a performance where the audience is naturally moving toward the exits. If you wanted everyone to return to their seats, you would have to persuade them to move in the opposite direction from the one they were already taking. That requires effort. A rechargeable battery is not literally a crowd of people being sent back to assigned seats, but the comparison helps. During discharge, the chemistry naturally tends to move toward a lower energy condition. During charging, the external power source forces the system back toward a higher energy condition. The charger provides the energy required to make that happen. Once the particles have been rearranged, the battery is ready to move back toward the lower energy condition later. Connect it to a phone, lamp, motor, or some other device, and the preferred chemical reactions can proceed in a direction that sends electrons through the external circuit. Those moving electrons are what allow the device to do useful electrical work. This means that charging is better understood as resetting a chemical system than filling a container. The materials inside the cell already contain the particles needed for the process. The charger reorganizes them. In many lithium-ion batteries, lithium ions move from one electrode material into another during charging. The electrode structures are designed so that lithium can enter and leave them repeatedly. You can think of these materials as having microscopic locations where lithium can be accommodated. When the battery charges, the lithium ions are driven toward one side and become incorporated into the structure there. When the battery discharges, they travel back in the opposite direction. The electrons take the outside route through the circuit because the internal separator prevents the battery from simply cancelling everything out immediately. This separation of paths is crucial. If the electrons could cross internally just as easily as the ions, the stored energy would be released inside the battery, rather than being available to travel through your device. That outside route is where the battery becomes useful. Suppose the charged battery is connected to a small light. The chemistry inside begins moving toward its lower energy condition. Lithium ions travel internally through the electrolyte, while electrons are pushed through the wire and through the light. The light makes use of the energy carried by that electrical process before the electrons complete their journey. In a phone, the route is considerably more complicated. The energy may pass through circuits that regulate voltage, operate the processor, power the display, produce sound, transmit radio signals, write information to memory, and keep track of the fact that the battery itself is becoming less charged. The device can perform all of those tasks because the battery chemistry creates conditions that drive electrical current through the external circuit. When the battery is charging, the direction of this process is reversed by the charger. The charger supplies electrical energy from outside and uses it to push the battery chemistry away from the state it would prefer to occupy. This is why charging requires a voltage supplied by an external source. Without that push, the battery would not spontaneously reorganize itself into a more energetic state, any more than a ball at the bottom of a hill would spontaneously roll uphill and wait there for later. If you want the ball higher, you must provide energy. If you want the battery returned to its charge condition, you must provide energy there as well. The ball comparison is useful, but batteries store energy in a much more complicated way than simple height. Chemical energy depends on how electrons are associated with atoms and molecules, how ions are positioned, how charges interact, and which arrangements are more or less energetically favourable. The battery materials are chosen so that these differences can be used repeatedly. During charging, the external circuit changes the distribution of electrons and drives ions into positions associated with a higher energy state. During discharge, the system can move back toward a lower energy state, releasing energy in the process. The energy is therefore tied to the complete arrangement and interaction of the materials. It is not sitting in one electron-like luggage in a suitcase. It belongs to the state of the battery as a whole. This is also why chemical language can sometimes make batteries sound more mysterious than they are. Terms such as oxidation, reduction, electrode potential, intercalation, and electrolyte are useful if you're designing batteries or studying electrochemistry. But the central picture can be understood without carrying an entire chemistry textbook into bed. One part of the battery has a stronger tendency than another to participate in certain electron transfers. The materials and internal structure are arranged so that the resulting chemical tendency can push electrons through an external circuit. Charging uses outside energy to reverse that tendency. Discharging lets the battery move back in the direction that releases energy. The details are sophisticated, but the basic logic is wonderfully practical. Store energy by forcing the system into a less relaxed arrangement, then recover some of that energy when the system returns. Of course, no real battery performs this process perfectly. Some of the electrical energy supplied during charging becomes heat rather than stored chemical energy. You may have noticed this if your phone or laptop feels warmer while charging. Part of that warmth comes from electrical resistance in the battery and charging electronics. Part can come from the chemical processes themselves. Energy is being moved through materials that are not perfectly efficient, and some of it ends up as random molecular motion, which we experience as heat. A good battery and charger try to keep these losses under control, but they cannot eliminate them entirely. This is why the amount of energy taken from the wall is somewhat greater than the amount later available from the battery. Nature rarely provides perfectly efficient bookkeeping, although it remains extremely strict about the total energy still being accounted for somewhere. The warming also gives us another clue about why battery charging must be carefully controlled. Moving ions and changing chemical states cannot simply be done as fast as possible without consequences. If the charging process is pushed too hard, unwanted reactions can occur. Materials can be damaged, heat can build up, the internal structure of the electrodes can degrade. This is why modern devices contain battery management systems that constantly monitor conditions while charging. They regulate how much current is allowed to flow, reduce the charging rate as the battery approaches its upper limit, and stop the process when continuing would become harmful. The little message saying that a device is charging may look simple, but behind it is a fairly careful negotiation between speed, temperature, chemical stability, battery life, and safety. Near the beginning of charging, many batteries can accept energy relatively quickly. As they approach their fully charged state, the process often slows. This is not because the final few percent are physically located somewhere difficult to reach, like socks at the back of a drawer. The slowdown happens because the electrical and chemical conditions inside the cell change as the state of charge rises. The charging system must become more cautious. Pushing too hard near the upper limit can place greater stress on the battery materials and encourage unwanted reactions. So the charger gradually adjusts what it is doing. This is why a phone might move from low charge to a high level fairly quickly, but spend noticeably longer completing the final portion. The same chemical reality explains why rechargeable batteries wear out with age. In a perfect imaginary battery, the internal particles could move back and forth forever with no permanent changes. Real materials are less cooperative. Each charge and discharge cycle can produce tiny structural changes. Some lithium can become trapped in places where it no longer participates efficiently. Layers can form on electrode surfaces. Repeated expansion and contraction can damage microscopic structures. Side reactions consume small amounts of useful material. Over hundreds or thousands of cycles, these changes reduce how much energy the battery can store and how easily ions can move through it. The battery that once powered a device all day may eventually begin asking for a charger by lunchtime, despite remembering a younger and more energetic version of itself. This aging process is important for our original question, because it reminds us that the phrase full battery does not always mean the same quantity of stored energy. A new battery at full charge may contain more usable energy than an old battery at full charge. Both can display a full indicator because each has reached the upper limit that its present condition allows, but the older cell may have lost part of its original capacity. If we could measure the mass difference associated only with stored energy, the newer battery could gain slightly more mass between discharged and charged states simply because it can store more energy. The effect would still be extraordinarily small, but the principle remains consistent. The amount of added mass depends on the amount of energy that has actually been stored, not on what the icon happens to show. There is also an important distinction between electrical charge and stored energy. Two objects can carry electric charge without functioning as batteries. Static electricity on a balloon is an obvious example. Rub the balloon on certain materials and electrons can be transferred, leaving a net imbalance of charge. That is quite different from the controlled electrochemical storage inside a rechargeable battery. A working battery is designed to maintain a difference in electrical potential between its terminals while remaining close to neutral overall. The battery can then drive electrons around an external circuit because its internal chemistry supports that separation of energy and charge. The important resource is not simply the number of electrons present, it is the energy available because of the battery's chemical state and the way charges are arranged. This becomes clearer if you imagine disconnecting a fully charged battery and leaving it on a shelf. The electrons do not all immediately rush out because there is no complete external path for them to follow. The battery remains in its higher energy chemical state. Over time, some energy may gradually be lost through self-discharge and internal reactions, but a good battery can retain much of its stored energy for a considerable period. The battery is therefore not storing a stream of electricity that somehow pauses when the cable is removed. It is storing the ability to produce electrical energy later. The current begins when a circuit provides a route and the chemistry is allowed to proceed. A tank of water on a hill offers another helpful comparison. The water is not flowing while the valve is closed, but the system can produce a flow because the water has stored gravitational energy due to its position. Open a route downhill and the water moves. A battery is similar in the limited sense that the charged state creates the ability to drive a flow when a path becomes available. Instead of water moving downhill under gravity, electrons move through an external circuit because of electrical and chemical conditions maintained by the battery. When the battery discharges, those conditions gradually weaken until the cell can no longer provide the useful voltage required by the device. Notice what has happened to our idea of a full battery. We began with something that sounded almost like a container filled with invisible fuel. Now the picture is different. The battery contains nearly the same material before and after charging, but that material has been placed into a different internal state. Ions have shifted, electron distributions have changed, chemical relationships have been altered, energy has been supplied from outside to create and maintain that arrangement. The The charged battery is therefore a physical system with more stored energy than the discharged battery. That is the point where the tiny increase in mass begins to make more sense. The charger does not need to add a noticeable amount of matter, because the extra mass is associated with the higher energy of the new configuration. When the battery is charged, the complete system has more energy than it had before. When it's discharged, some of that energy is left and spread into the device and surroundings. The atoms do not need to disappear for the mass to change. The total energy of their arrangement has changed. There is a subtle detail worth keeping in mind. During ordinary charging, tiny amounts of material can sometimes enter or leave a real battery through side effects, contamination, gas formation, or other imperfect processes, especially as cells age or become damaged. But those effects are not the reason a correctly operating battery is fundamentally more massive when charged. Even an ideal sealed battery that exchanged no matter at all with its surroundings would still gain mass when energy was stored in it. That is the clean physical idea we are following. The same logic applies even if the battery were charged without an ordinary wall socket. Suppose sunlight falls on a solar panel, which powers a charger, which transfers energy into the battery. Energy originally carried by light ends up stored in the battery's chemical configuration. The battery becomes more massive by a tiny amount because it now contains more energy. If the battery later powers a lamp, that stored energy leaves again, eventually becoming light and heat in the environment. The battery loses the corresponding tiny amount of mass. The route can involve sunlight, wires, chemical reactions, electronics, and warm air. But the accounting remains connected from beginning to end. This is one reason batteries are such a useful doorway into a much larger idea. They show us that energy storage is not an abstract label we attach to an object. Something physically different is true about a charged battery compared with a discharged one. The positions and chemical states of particles are different. The possible reactions are different. The ability to drive electrical current is different. The total energy is different. And because the total energy is different, the mass is different too. We are now close to the deeper part of the question, because saying that a charged battery contains more energy still leaves us with another problem. What does it mean for stored energy to contribute to mass? Why should a chemical arrangement inside a battery have anything to do with how strongly gravity pulls on the object, or how difficult the object is to accelerate? A battery does not look heavier when charged, and nothing about the moving ion seems large enough to explain a change in mass by ordinary intuition. To understand that connection, we have to look more carefully at where the stored energy belongs, and why physics treats energy inside a system as part of the mass of that system. That question takes us away from the simple idea of particles moving from one side of a battery to the other, and into something slightly more subtle. If charging rearranges the materials already inside the battery, then where exactly is the added energy? It is tempting to imagine that it must be hiding somewhere specific. Perhaps the electrons carry it. Perhaps the lithium ions carry it. Perhaps there is some microscopic region inside the battery that becomes packed with energy, while another region empties out. Our everyday experience encourages this kind of thinking, because most things we store have a location. Water sits in a tank, food sits in a cupboard, petrol sits in a fuel tank, biscuits sit in a tin until someone discovers them. Stored energy is different. In a battery, it does not belong neatly to one object or occupy one little pocket. The extra energy is associated with the arrangement of the entire electrochemical system, and with the interactions between the particles that make up that system. A useful way to approach this is to return to the idea of a ball on a hill. Imagine a ball resting at the bottom of a gentle slope. Left alone, it is perfectly content to remain there. If you want the ball at the top, you have to provide energy by pushing or carrying it upward. Once it reaches the top, the ball has not become a different ball. It has not absorbed a new collection of atoms. What has changed is its position relative to the Earth. Because of that arrangement, the system now has the ability to release energy. Let go of the ball and gravity can accelerate it downhill. The energy we stored by lifting the ball appears as motion. The important point is that the stored energy is connected to a relationship. It belongs not simply to the ball and not simply to the earth, but to the arrangement of the ball and the earth together. Inside a battery, the situation is far more complicated, but that idea of energy belonging to an arrangement is extremely useful. During charging, ions are moved into different positions within the electrode materials, electrons are redistributed through the external circuit, and chemical relationships are changed. The charged arrangement has more energy than the discharged arrangement. When the battery is later connected to a device, the system can move toward a lower energy condition and transfer some of that difference through the circuit. The energy is not hidden inside individual electrons like tiny parcels waiting to be delivered. Instead, it is associated with how the electrons, ions, atoms, electric fields, and chemical structures relate to one another. This matters because electrons themselves are present whether the battery is full or empty. A discharged battery does not suddenly run out of electrons. If it did, it would be in a very unusual electrical condition, and probably not something you would want inside your phone. The same is true of the lithium ions in a lithium-ion battery. They do not disappear when the battery is discharged and then return from the charger when it is charged. They remain part of the battery. What changes is where they are, and what chemical environment they occupy. That change in environment changes the energy of the complete system. Imagine 2 rooms in a building connected by a corridor. The same group of people can be arranged differently between the rooms. Perhaps one room is easy to stand in while the other requires everyone to climb onto awkward platforms. Moving people into the awkward room requires effort. Once they are there, the arrangement contains a kind of stored possibility, because everyone would quite happily climb back down if given the chance. The number of people has not changed, but the state of the system has. A rechargeable battery does something loosely comparable at the microscopic level. Charging pushes particles into arrangements that require energy to establish. Discharging allows the system to move toward arrangements that are more energetically favourable, while the difference is transferred outward. The word chemical can sometimes make this sound as though the energy must be stored in individual chemical bonds, and people often hear the phrase chemical energy and picture bonds as tiny springs packed with energy. That picture can be useful in very simple explanations, but it is incomplete. Breaking a chemical bond actually requires energy. Energy is released when new, more favourable interactions and bonds form as part of an overall reaction. What matters is the energy difference between the complete starting arrangement and the complete final arrangement. A battery works because its materials can participate in reactions and rearrangements where one state has more available energy than another. Charging uses outside energy to rebuild the higher energy state. This is why asking where the energy is stored does not produce the same sort of answer as asking where the electrolyte is stored. The electrolyte occupies a physical region. The electrode material occupies a physical region. The separator occupies a physical region. The energy is a property of the state of all those things together. You can certainly describe contributions coming from particular chemical and electrical interactions, but there is no little container-marked stored energy that becomes fuller as the charging indicator rises. Electric fields also belong in this story. Whenever electric charges are arranged in particular ways, there can be energy associated with the resulting electric field. The simplest example is not even a battery. Imagine 2 objects carrying opposite electric charges and being pulled apart. Because the charges attract each other, separating them requires work. If you hold them apart, the system now has stored energy. Release them, and they can move back together, turning that stored energy into motion. Once again, the energy is associated with an arrangement and an interaction, rather than being a substance sitting inside one of the objects. Batteries create and maintain differences in electrical potential through chemistry. The internal reactions influence how strongly electrons tend to move through a connected circuit. During charging, an outside power source drives those chemical and electrical conditions in the opposite direction. The battery ends up in a state where it can later push electrons around an external path. The electric field in the circuit helps establish that motion extremely quickly. When the circuit is connected, while the battery chemistry continues to maintain the conditions required for current to flow. This is worth mentioning because another common mental picture suggests that electrons leave the battery and then race all the way through a long wire, carrying energy directly from the battery to whatever device is waiting at the other end. Electrons do move through the circuit, but the transfer of electrical energy involves the electromagnetic fields associated with the circuit as well. The individual electrons in a metal wire drift much more slowly than the response of the circuit might suggest. Turn on a lamp, and you do not have to wait for one heroic electron to travel from the battery through every centimetre of wire and finally arrive at the bulb. The electric field throughout the circuit adjusts rapidly, and energy is transferred through the electromagnetic system, while charges in the conducting material respond locally. That may sound like we have wandered away from the battery, but it helps remove the idea that energy must always travel by attaching itself to a particular particle. Physics does not require energy to behave like a microscopic suitcase. Energy describes the capacity of a physical system to produce change, and it can be associated with motion, fields, positions, chemical arrangements, heat, radiation, and many other aspects of a system. A battery is useful because it converts between these forms in a controlled way. While charging, electrical energy arrives from the charger. Some becomes heat, which is generally the part we would prefer to keep small. The rest changes the battery's electrochemical state. Later, during discharge, that stored electrochemical energy becomes electrical energy in the external circuit. The phone or laptop then transforms it again. Some becomes light from the display, some becomes sound, some powers radio transmissions, some becomes temporary electrical states inside processors and memory. Almost all of it eventually ends up as heat dispersed into the surroundings. If you followed the energy long enough, the neat little package that entered the battery from the charger would gradually spread into a huge number of microscopic motions and interactions in the environment. The battery gives us temporary control over that process. Instead of allowing the incoming electrical energy to become heat immediately, we use it to create an internal state that can persist. That persistence is one of the remarkable features of battery chemistry. A charged battery can be disconnected and left alone, yet much of the higher energy arrangement remains. The particles do not instantly return to the discharge configuration because the reactions require particular pathways, and those pathways can be limited when there is no complete external circuit. The battery is therefore able to hold an energetically favourable opportunity in reserve. Consider a rock sitting near the edge of a shelf. The rock can remain there for a long time even though it could release gravitational energy by falling. The fact that a lower energy state is available does not mean the system must reach it immediately. Something may prevent the transition. The rock needs a path off the shelf. The battery also requires suitable pathways for its internal reactions and electrical current. Disconnect the circuit and the energy can remain stored for a considerable time, although real batteries slowly lose charge through internal processes. This idea of barriers is important throughout chemistry. Many materials around you contain energy that could be released through chemical reactions, but those reactions do not necessarily happen quickly. A wooden table can react with oxygen and release energy as heat and light, yet it usually does not burst into flame during breakfast. There is an energy barrier that must first be overcome. Once enough heat is supplied, combustion can proceed much more rapidly. Battery chemistry is obviously designed to be much more controlled, but the broader lesson is that knowing which state has less energy does not tell you how quickly a system can get there. Rechargeable batteries are engineered so that their important chemical changes can be reversed many times. During charging, energy is used to drive the materials toward one arrangement. During discharge, they move back toward another. Ideally, very little material is permanently altered along the way. Reality is less tidy. Small side reactions occur. Electrode structures change slightly. Some ions become unavailable. Surfaces develop new layers. The battery gradually becomes less capable of returning perfectly to its original charge condition. This is one reason an old battery stores less energy than a new one even when both are described as fully charged. The amount of energy stored therefore depends on the difference between the battery's internal states, not merely on the physical size of the cell. Two batteries of similar mass can store very different amounts of useful energy if their chemistry and design differ. Engineers spend enormous effort trying to increase the amount of energy that can be stored for a given battery mass, while maintaining safety, long life, reasonable cost, fast charging, and reliable performance. Improving one of those qualities can make another more difficult. A battery that stores a great deal of energy in a small space is useful, but it also means that more energy is available if something goes badly wrong. This is why battery design is always a compromise rather than a simple race to pack in as much energy as possible. At the microscopic level, much of the story comes down to electrons preferring some arrangements over others. Electrons in atoms and materials can occupy different energy states depending on their surroundings. When chemical reactions rearrange atoms and electrons into states with lower total energy, the difference can be released. When charging reverses those reactions, outside energy must be supplied to move the system back toward the higher energy condition. Lithium is especially useful in rechargeable batteries because of its chemical properties and its low atomic mass, but the energy does not simply reside in the lithium itself. It emerges from the difference between complete arrangements involving lithium, electrode materials, electrons and their interactions. Suppose you could somehow freeze a charged battery and inspect every particle without disturbing anything. You would find atoms, electrons and ions in definite microscopic environments. Then imagine doing the same with the battery after it had discharged. Many of the same particles would still be present, but they would be distributed differently between the materials and would occupy different chemical states. If you could calculate the total energy of every interaction in each case, the charged arrangement would have the greater total energy. That difference is what the battery can give back. The idea becomes even easier to see if we compare a battery with a stretched rubber band. When you stretch the rubber band, you do not pour energy into a hollow compartment. You change the arrangement of the long molecular chains that make up the rubber. The stretched state can later pull back because another arrangement is more favourable. The stored energy belongs to that distorted configuration. A battery differs in almost every practical detail, but both systems demonstrate that an object can store energy through the way its internal components are arranged. A compressed gas offers another variation. Imagine a sealed cylinder containing gas. Compress the gas with a piston, and you transfer energy into the system. The molecules become confined differently, collisions become more frequent, and the gas may also warm. The cylinder can later push the piston outward and perform work. Once again, the same basic collection of particles can occupy states with different total energies. The physical system has not needed to acquire a new category of substance called energy. Its state changed. For batteries, this distinction becomes especially important when we return to the question of mass. If we still imagine charging as adding extra electrons, we might try to explain the increased weight by calculating the mass of those extra electrons. But that would miss the real effect. The battery's increased mass comes from the increased energy of the system as a whole. Even if no net electrical charge were added to the sealed battery, and even if exactly the same number of electrons, protons, neutrons and atoms remained inside before and after charging, the charged battery would still have greater mass because its total internal energy would be greater. There is something counterintuitive about saying that the same particles can weigh differently depending on their arrangement. Our instinct tells us that mass should be something each particle brings with it, rather like every passenger bringing a suitcase onto a train. Add up the passengers and suitcases and you have the total. But physical systems are not always that simple. The energy associated with the relationships between the parts also contributes to the mass of the whole. Sometimes rearranging the same components increases the total energy and therefore increases the mass. In other situations, assembling particles into a bound system releases energy, leaving the finished system with less mass than the separated components had. Even ordinary chemistry contains this principle. although the changes are far too small for normal chemical balances to reveal directly. If a chemical reaction releases energy, and that energy escapes from the system as heat or light, the products left behind have slightly less mass than the starting materials did before the energy escaped. If you reverse the reaction and supply the energy again, the mass increases. Chemists usually do not need to include that difference in routine measurements, because it is so tiny compared with the masses involved, but nature includes it whether the laboratory worksheet does or not. A rechargeable battery repeatedly moves between two such chemical conditions. When we charge it, we supply energy and restore the higher energy arrangement. When we discharge it, the battery transfers some of that energy to the outside world and moves toward the lower energy arrangement. The mass rises and falls along with that stored energy, even though the ordinary material remains essentially the same. There is also no need to imagine that the extra energy is uniformly spread through every millimetre of the battery. Different interactions contribute in different places, and real cells contain complicated structures with varying local electric fields, chemical compositions, and charge distributions. The meaningful statement is that the total energy of the complete battery is higher when charged. When we place the whole sealed battery on a scale, the scale does not need to know which microscopic interaction contributed which tiny portion. It responds to the mass of the entire object. This gives us a more precise way to understand the word stored. Stored energy does not necessarily mean a substance has been physically collected somewhere. It means the system has been placed in a state from which energy can later be transferred. A lifted object stores gravitational energy. A stretched spring stores elastic energy. A charged capacitor stores energy associated with an electric field. A hot object contains more thermal energy. A battery stores energy in its electrochemical configuration. These mechanisms look different, but each allows one physical state to contain more energy than another. The battery beside you is therefore not just a container with a certain amount of invisible fuel remaining. It is a complex arrangement of matter whose internal state determines how much energy can still be transferred through a circuit. When the battery indicator falls, the device is not counting individual electrons disappearing into the screen. It is estimating how far the electrochemical system has moved from its charged state toward its discharged state, and how much useful energy is likely to remain available. This also explains why battery indicators are sometimes imperfect. The device cannot simply look inside and count pieces of stored energy. It has to infer the state of charge from electrical measurements, past current flow, voltage behavior, temperature, battery age, and models of how the particular cell behaves. When an old phone suddenly falls from a comfortable remaining charge to almost empty, the laws of physics have not changed their minds. The estimation has simply encountered a battery whose real condition no longer matches the simplified model quite as neatly as it once did. By now, the location of the extra energy should seem less mysterious, although perhaps not in the way we first expected. It is not located in one special particle, one chemical bond, or one hidden compartment. It is encoded in the higher energy configuration of the battery's components and their interactions. Charging builds that configuration. Discharging allows it to relax. The difference between those states is what powers the device. That brings us directly to the part of the story that sounds almost absurd when heard for the first time. If the charged battery contains the same basic matter, but has more energy because of its arrangement, why should a scale care? Why should stored chemical energy have anything to do with mass at all? The answer takes us beyond batteries and into one of the most famous changes in our understanding of matter, where energy and mass stop behaving like completely separate entries in nature's accounting and turn out to be deeply connected. Once we accept that charging a battery changes the energy of its internal arrangement, the next question is unavoidable. Why should that make the battery heavier? After all, energy does not look like matter. You cannot pour it into a bowl, place it beside a ruler, or accidentally leave some of it in your coat pocket. A battery can gain energy without gaining any noticeable amount of new material, so it seems reasonable to expect its mass to stay exactly the same. That expectation would have fitted comfortably into older ideas about physics, where mass and energy were usually treated as separate quantities. Mass belonged to objects, energy described what those objects could do. Then, in the early 20th century, Albert Einstein helped change that picture completely. One of the consequences of his work was that mass and energy are not independent pieces of nature's accounting. The energy contained within a system contributes to the mass of that system. Put more energy into a closed object and, all else being equal, the mass of the object increases. Remove energy and the mass decreases. Your charged battery is a small and extremely ordinary example of that connection. This idea is often introduced through Einstein's famous relationship between mass and energy, but we do not need to write it down to understand what it means. The important part is that a certain amount of mass corresponds to an enormous amount of energy. This is why nuclear reactions can release so much energy when only a very small amount of mass changes. It is also why the opposite effect, the extra mass created when we store an ordinary amount of energy, is so difficult to notice. The connection works both ways. A very small change in mass can correspond to a great deal of energy, and a useful but ordinary amount of stored energy corresponds to an extremely small change in mass. A phone battery can store enough energy to power a device for hours, yet the increase in mass when that battery is charged is vastly smaller than anything your hand could detect. The easiest way to understand the idea is to stop thinking of mass as simply the amount of material inside an object. That definition is useful for everyday life, but modern physics gives us a deeper one. The mass of a complete system depends on the total energy contained within that system when considered as a whole. That includes the energy associated with the particles themselves, but it also includes energy connected with motion inside the system, chemical arrangements, electric fields, heat, binding between particles, and other internal processes. If the total internal energy changes while the system remains otherwise contained, its mass changes as well. Consider a sealed box containing a spring. Imagine weighing the box while the spring is relaxed. Then, without adding or removing any matter, a mechanism inside the box compresses the spring and locks it in place. The compressed spring stores more energy than the relaxed spring. The sealed box now has slightly more mass. The number of atoms inside has not increased. The metal in the spring is still the same metal. The walls of the box are still the same walls. What changed was the internal energy of the system. If the spring is later released and its energy becomes heat inside the sealed box, the total mass of the closed box remains the same because the energy is still inside, only in another form. If that heat is then allowed to escape into the room, the box loses energy, and its mass decreases by a tiny amount. That final detail is important because it shows that mass does not care very much about the form the energy takes. Stored elastic energy in a spring contributes to the total mass. Thermal energy contributes. Chemical energy contributes. Electrical energy contributes. If energy remains within the boundaries of the system we are weighing, it is part of the mass of that system. If energy leaves, the mass falls accordingly. A battery behaves in the same general way. When you charge it, electrical energy arrives from outside. Much of that energy becomes stored in the electrochemical configuration we discussed earlier. Some may temporarily become heat, but if we imagine the battery cooling back to the same temperature before comparing its charged and discharged states, the charged battery still contains more energy because its chemistry has been pushed into a higher energy arrangement. That extra internal energy means the charged battery has more mass. There is no requirement for the energy to be sitting still in a little compartment. Suppose instead that we had a perfectly reflecting sealed box containing light. Light is especially interesting because individual particles of light do not have rest mass in the way electrons or protons do. Yet if you trap light inside a closed box, the total mass of the box and its contents is greater than the mass of the same box without that light. The light carries energy and momentum, and those contribute to the properties of the complete system. Release the light and allow it to escape, and the box becomes slightly less massive. This is a useful reminder that the mass of a system cannot always be understood by simply adding up the rest masses of the individual particles inside it. The same lesson appears when we look at atoms. You might imagine that the mass of an atom should be exactly equal to the masses of all its protons, neutrons, and electrons added together. In reality, the total mass also depends on the energy associated with how those particles are bound together. When particles form a stable bound system and energy is released, the finished system can have less mass than the separated ingredients had before. The missing mass has not vanished mysteriously. It left as energy during the formation of the bound system. If you wanted to separate those particles completely again, you would have to supply energy, and the mass of the full system would increase as that energy was restored. This may sound like the opposite of what happens in a charged battery, but it is actually the same principle. In both cases, more total energy means more total mass. If a system releases energy and that energy escapes, its mass decreases. If energy is supplied and retained, its mass increases. The direction of a chemical reaction or a nuclear process does not change the rule. What matters is the total energy of the system before and after. This is where the phrase energy has mass needs a little care. It is useful shorthand, and it captures the main idea, but it can also encourage the thought that every bit of energy behaves like a tiny object carrying a fixed lump of mass. Physics is subtler than that. The safer way to say it is that energy contributes to the mass of a system. A moving particle, for example, has more energy when it moves faster, but physicists usually do not say that the particle's own rest mass grows simply because it is moving. Instead, we consider the total energy and momentum of the system involved. For a battery sitting on your table, however, the practical conclusion is simple. Add internal energy while keeping the battery as a complete object, and its total mass increases. The word rest is useful here because when we talk about the mass of your phone or battery, we mean the mass measured when the object as a whole is not moving relative to us. Inside the battery, particles are always moving. Atoms vibrate. Electrons occupy quantum states. Ions may move during charging or discharging. Thermal motion continues even when the battery is sitting peacefully on the table. All of that internal activity contributes to the total energy of the system. The phone itself does not need to be racing across the room for its internal energy to affect its mass. Heating gives us one of the clearest everyday examples. Take two otherwise identical sealed metal boxes, keep one cooler, and heat the other. The warmer box has more internal thermal energy and therefore slightly more mass. If both boxes are later allowed to reach the same temperature, that difference disappears because the warmer one releases energy into its surroundings. Nobody notices the associated mass change in ordinary life because it is tiny, but it follows the same physics as the battery. A wound clock provides another example. Imagine an old mechanical clock powered by a spring. When you wind it, you transfer energy from your muscles into the spring mechanism. The wound clock has slightly more mass than the same clock after it has run down. As the clock operates, the spring releases energy. The gears move, friction produces heat, and some sound escapes into the room. Once that energy has left the clock's mass has fallen by an incredibly small amount. The clock did not lose gears or screws, it lost internal energy. The battery in your pocket is doing something comparable, although with electrochemistry rather than a wound spring. Plugging in the phone transfers energy into the device. The battery stores much of it by rearranging its internal chemical state. Once fully charged and allowed to return to the same temperature as before, the phone has slightly more mass than it did when the battery was discharged. Later, while you use the phone, energy leaves the battery and is transferred into the electronics. The display emits light. The speaker produces sound. Radio waves leave the antennas. Heat spreads into your hand and the surrounding air. As energy leaves the complete phone, the phone's mass decreases. You might now wonder whether the phone also becomes lighter every time it sends out a radio signal or emits light from the screen. In principle, yes. Those forms of energy carry energy away from the device, so the mass of the remaining device decreases by a corresponding tiny amount. Of course, the battery chemistry is supplying that energy at the same time, so we normally describe the process as the battery discharging. But if you could follow every bit of energy, you could trace the mass change along with it. This does not mean that energy turns into a mysterious cloud of weight when it enters the battery. Weight and mass are related but not identical. Mass is an intrinsic property of the complete system, while weight describes the gravitational force acting on that mass in a gravitational field. On the surface of Earth, if the mass of the battery increases, its weight also increases by the corresponding tiny amount, because Earth pulls gravitationally on the slightly more massive system. Take the same charged battery to the Moon, and its mass would remain the same, while its weight would be smaller, because the Moon's gravity is weaker. So when we say a charged battery weighs more, we're using ordinary language for the fact that its mass has increased and therefore gravity pulls on it a little more strongly in the same location. The increase is not caused by gravity. Even if you imagine the battery floating far away from planets and stars, its charged state would still have more mass than its discharged state. Gravity simply gives us one possible way to detect that difference by measuring weight. Another possible method would be to measure how resistant the object is to acceleration. More mass means a slightly greater resistance to being accelerated by the same force. Again, the difference for a battery is so small that this would be an almost hopeless way to notice it in practice, but the principle remains. Einstein's contribution becomes particularly striking here because this is not an effect reserved for exotic nuclear reactions. People often encounter the connection between mass and energy in discussions of stars, atomic bombs, particle accelerators, or the enormous energy released inside the sun. Those are dramatic examples because the energy changes involved are large enough to produce effects we can easily observe, but the underlying relationship is universal. It applies to a cup of hot tea, a compressed spring, a rotating flywheel, a charged capacitor, a wound watch, and the battery in your phone. The reason nuclear physics makes the connection look much more impressive is that nuclear processes can involve changes in internal energy far larger than those in ordinary chemistry. The forces holding atomic nuclei together operate at energy scales very different from the chemical interactions used by batteries. When a nuclear reaction releases energy, the associated mass difference can become large enough to measure quite directly. Chemical batteries live at much smaller energy scales, so their mass changes are correspondingly smaller. The rule does not become weaker. The amount of energy involved is simply much less. There is something useful about recognizing this because it stops us from dividing the universe into matter on one side and energy on the other, as though they belong to completely separate categories. A battery is made of matter, but its mass depends partly on its internal energy. A beam of light is not matter in the ordinary sense, yet trapping that light changes the mass of the system containing it. A stable atomic nucleus can weigh less than its separated ingredients because energy was released when the bound state formed. These examples are different expressions of the same deeper accounting. The battery also helps us avoid another misunderstanding. When people first hear that energy contributes to mass, they sometimes imagine that charging must somehow create new particles. It does not. The increased mass does not require new protons, neutrons, or electrons to appear. The particles already inside can form a system with different total masses, depending on how much energy the complete system contains. That is exactly what makes the result so surprising. We are used to treating particles as the only things that count toward mass. Physics tells us that the energy of their arrangement counts too. Imagine a perfectly sealed container holding two magnets. In one configuration, the magnets are arranged so that they strongly want to move toward each other. A mechanism inside the container pulls them apart and locks them in place, using energy to do so. The sealed container now stores more energy and has slightly more mass. Nothing entered the container. No extra iron appeared in the magnets. The difference comes from the changed internal state. Release the magnets and allow the stored energy to become heat inside the sealed box, and the total mass remains the same as long as the heat stays inside. let the heat escape, and the box becomes lighter. That detail can initially seem strange. If the magnets slam together and the stored energy becomes heat, surely the stored energy has been used up. In everyday language, yes, because it is no longer available in the same useful form. But from the point of view of total energy, it has not disappeared. It has merely changed form. As long as all that heat remains trapped inside the box, the total energy, and therefore the total mass, remain unchanged. Only when energy crosses the boundary and escapes does the mass of the box decrease. The same reasoning applies to a battery that has just been discharged rapidly and is still warm. If we compare it immediately with a cool charged battery, temperature can complicate the simple statement that the charged battery is heavier. Some of the energy that used to be stored chemically may now remain inside the discharged battery temporarily as heat. To make a clean comparison, we should compare the charged and discharged battery at the same temperature and under the same conditions. Then the difference in stored electrochemical energy is what matters. This is one reason careful physics experiments can become surprisingly fussy. A statement that sounds as simple as a full battery is heavier than an empty. One suddenly requires us to ask whether the batteries have the same temperature, whether any gas escaped, whether moisture changed, whether the casing expanded, whether the scale warmed up, and whether the person doing the experiment leaned on the table. At ordinary scales, these details hardly matter. At the scale of the mass difference produced by battery energy, they matter enormously. There's another useful way to think about the size of the effect. Imagine taking the energy stored in a phone battery and converting all of it into the equivalent amount of mass. You would not get anything resembling a grain of sand. You would not even get something comfortably visible under a normal microscope. The corresponding mass is fantastically smaller than that. This is why charging a phone does not make your pocket sag lower, and why electric cars do not become noticeably harder to move after charging their enormous battery packs. An electric car battery stores vastly more energy than a phone battery, so its mass increase when charged is also much larger than the phone's increase. Even then, it remains tiny compared with the mass of the vehicle. You could fill the battery with enough energy to drive for hundreds of kilometers and still not notice the mass change with any normal vehicle weighing system. The car may gain far more apparent weight from a bottle of water left in the cup holder than from the entire electrical charge stored in its battery. Yet the tiny size of the effect should not make us dismiss it as merely theoretical. Our inability to feel something does not decide whether nature includes it. Relativity itself is full of effects that become obvious only under precise conditions. Clocks at different heights tick at slightly different rates because gravity affects time. Fast-moving clocks tick differently from slower ones. Satellite navigation systems must account for relativistic effects, even though nobody sitting in a car feels time behaving strangely. The universe does not adjust its rules to match the sensitivity of human senses. Your battery follows those same rules. As energy enters, its total mass rises. As energy leaves, its mass falls. The difference is small because ordinary chemical energy is small compared with the enormous energy associated with even a modest amount of mass. That is the reason the effect can be both completely real and almost impossibly difficult to notice. The next natural question is therefore not whether a charged battery becomes heavier, but by how much. If we took a familiar phone battery, measured the amount of energy it can store, and translated that energy into the corresponding increase in mass, what kind of number would we get? Would it be merely small, or so small that even the word tiny begins to look overly generous? That calculation is where the scale of Einstein's connection becomes much easier to appreciate, because the answer shows just how much energy is hidden in even the smallest amount of mass. If the charge battery really is heavier, the next question is, how much heavier? This is where the story becomes both satisfying and slightly ridiculous, because the answer is not merely small. It is so small that nearly every object you encounter in ordinary life is enormous by comparison. The extra mass stored in a charge battery is real. but if you are hoping to prove it by placing your phone on a kitchen scale before and after charging, you would be asking the scale to notice something far beyond what it was designed to detect. The difference would be buried under effects as ordinary as a change in temperature, a trace of moisture on the casing, a small air current in the room, or perhaps one fingerprint left on the screen after you checked whether the battery had finally reached full. To get a sense of the scale, consider a typical modern phone battery. The exact capacity depends on the device, but a phone battery might store something in the neighbourhood of 15 watt-hours of energy when fully charged. Spoken in more familiar terms, that is enough energy to keep a small electronic device operating for many hours, depending on what the device is doing. It can illuminate the display, run the processor, transmit signals, play audio, take photographs, and perform all the quiet background tasks that continue whether you remember asking for them or not. From the point of view of a phone, this is a useful amount of energy. From the point of view of mass, however, it corresponds to only a tiny fraction of a billionth of a gram. For a battery storing around 15 watt-hours, the increase in mass between a fully discharged state and a fully charged state is roughly 6/10 of a nanogram. A nanogram is 1 billionth of a gram, so even one whole nanogram is already extraordinarily small. The battery gains less than that. 6/10 of a nanogram is far too little for you to see, feel, or measure with any normal household equipment. A single speck of dust can weigh vastly more. A fingerprint can add far more material than the mass gained from the stored energy. Even a tiny change in the amount of moisture clinging to the phone could overwhelm the effect. This gives us a useful perspective on what Einstein's connection between mass and energy really means in everyday life. We often hear that mass contains an enormous amount of energy, and this is the other side of the same statement. If even a tiny amount of mass corresponds to a huge amount of energy, then storing an ordinary amount of energy only creates an incredibly tiny amount of additional mass. The relationship is not weak. It is precisely because the relationship involves such a large conversion between the two that the mass increase is so difficult to notice. Take a small rechargeable battery used in a camera or another compact device. Suppose it stores only a few watt-hours. The mass it gains when charged would be only a small fraction of a nanogram. There is nothing wrong with the battery and nothing incomplete about the physics. The effect is simply operating at a scale where the ordinary disturbances of the physical world become gigantic by comparison. If you place the battery on an extremely sensitive balance, the warmth of your hand from touching it could create a larger measurement problem than the effect you were trying to observe. A laptop battery gives us a somewhat larger example. Many laptops store several times more energy than a phone. Suppose a battery stores around 60 watt-hours. That amount of energy can operate a computer for hours, depending on the workload, screen brightness, processor activity, wireless connections, and the mysterious enthusiasm of whichever application has decided to use half the system resources while apparently doing nothing. When that battery is fully charged, its extra mass from stored energy would be around a few nanograms. That is several times more than the phone battery, which makes sense because more stored energy means more additional mass. Yet it is still completely invisible in daily life. Several nanograms may sound less absurd than a fraction of one, but it is still extremely small. A grain of salt is vastly heavier. A dust particle can be heavier. A microscopic droplet of water can be heavier. If you cleaned the laptop screen, moved a crumb from the keyboard, or changed the amount of moisture absorbed by some part of the casing, you could alter the total mass by an amount enormously larger than the relativistic difference created by charging the battery. This is why nobody notices a laptop becoming heavier when it's plugged in. The effect is not merely below the sensitivity of your muscles. It is buried beneath ordinary changes in the object and its surroundings. The laptop can warm up as it charges. A cooling fan can move air. The battery materials can expand slightly. The charging cable can exert a small force on the machine. Even the table can vibrate as someone walks across the room. Compared with a few nanograms of mass change, these are not small inconveniences. They are overwhelming. Now consider something much larger, such as an electric car battery. A large vehicle battery can store tens of thousands of watt-hours rather than the few dozen found in a laptop. Suppose the battery stores around 75,000 watt-hours when fully charged. That is an enormous amount of energy compared with a phone battery. It is enough to move a heavy vehicle over a substantial distance while running computers, pumps, lights, climate control systems, and everything else the car requires. Surely with that much stored energy, the weight difference must finally become noticeable. It becomes larger, certainly, but not in the way you might expect. A battery storing around 75,000 watt-hours would gain only about 3 micrograms of mass when fully charged compared with its discharge state. A microgram is 1/1,000,000th of a gram, so 3 micrograms is still an extremely small quantity. The entire battery pack may weigh hundreds of kilograms, yet the contribution from the stored electrical energy is only a few millionths of a gram. You could drive a large electric vehicle onto a very accurate scale before charging, charge the battery completely, return under identical conditions, and the added mass from the stored energy would still be completely hidden by countless other changes. A few grains of road dust would overwhelm it. A small amount of water on a tire would overwhelm it. A difference in cabin humidity would overwhelm it. A dead insect on the front of the car would overwhelm it by an embarrassing margin. Even changes in the temperature of the vehicle would create far larger effects than the few micrograms associated with the stored battery energy. This comparison is useful because people sometimes wonder whether an electric car becomes significantly heavier after charging. It does become heavier in the strict relativistic sense, but the difference is nowhere near enough to affect driving range, tire pressure, suspension, handling, or anything else you would ever notice. The battery can contain enough energy to move the entire car for hours, yet the mass equivalent of that energy remains tiny. Imagine a much larger stationary battery used to store electricity for a building or electrical network. Suppose it stores several times more energy than an electric car battery. The mass difference might rise into the tens of micrograms, depending on the amount of stored energy. That is easier to say aloud than a fraction of a nanogram, but it is still tiny compared with the physical size of the equipment. A large battery installation could weigh many tons. The increase in mass from charging it might still be less than the mass of a small drop of water. This is one of those moments where our intuition about energy and our intuition about mass fail to line up. We see a large battery system capable of powering homes or moving vehicles and naturally think that the energy inside must have a substantial physical weight. It does have weight, but our idea of substantial is shaped by the mass of ordinary matter. The energy stored chemically in a battery is tiny compared with the energy already associated with the matter making up the battery itself. The battery casing, electrodes, electrolyte, current collectors, separators, and all the other components already possess enormous energy simply because they have mass. The additional chemical energy stored by charging represents only a very small change in the total energy of the system. That is why the relative mass increase is so tiny. Charging does not transform the battery into a fundamentally different object. It shifts the internal chemistry through a relatively modest range of energy, compared with the enormous energy already present in the matter itself. A comparison with food can help. A meal contains chemical energy that your body can release through metabolism. If you had a perfectly sealed container holding food and compared it before and after the chemical energy had been completely released and allowed to escape, the mass would differ by a tiny amount because energy had left. Yet when you weigh food, almost all of the mass comes from the matter itself, not from the usable chemical energy stored in its molecular arrangements. Batteries work on a similar scale of chemical energy. They are remarkable because they allow us to access that energy electrically and repeatedly, not because chemical storage produces large changes in mass. Nuclear processes are where the connection becomes much more obvious. The energy differences involved in nuclear binding can be much larger relative to the mass of the material. That is why nuclear reactions can release tremendous amounts of energy from comparatively small quantities of fuel. Batteries operate through chemical processes where the relevant energy differences are far smaller. So while the same fundamental relationship between energy and mass applies, the practical mass change is much more modest. There is another way to appreciate how tiny the battery effect is. Imagine trying to increase the mass of a phone battery by just 1 gram using stored energy alone. 1 gram sounds trivial. A small paperclip can weigh around that much. Yet storing enough energy to add an entire gram of mass would require an amount of energy utterly beyond what a phone battery could contain. The battery would fail in every possible practical sense long before approaching anything remotely close to that. The materials could not hold such energy. The device would not remain a battery in any recognizable form. 1 gram of mass represents an astonishing quantity of energy compared with the chemical energy we store in portable electronics. This is why 0.6 of a nanogram from a phone battery is not evidence that the connection between mass and energy is weak. It is evidence that even a tiny amount of mass represents a tremendous amount of energy. The small number is exactly what the physics predicts. You may also wonder whether different battery chemistries gain different amounts of mass when storing the same amount of energy. If 2 perfectly sealed batteries begin and end under comparable conditions, and both store exactly the same increase in total energy, then the corresponding increase in mass is the same, regardless of how that energy is stored. One battery might use lithium-based chemistry, while another uses a completely different chemical system. The microscopic details can be very different, but the total mass increase depends on the energy added to the system. Where chemistry matters is in determining how much energy a battery of a particular size and mass can store. Some battery designs store more energy per kilogram than others. A battery that can store twice as much usable energy in the same overall mass can also undergo roughly twice the relativistic mass increase between empty and full, assuming comparable conditions. Even then, both changes remain tiny. Temperature complicates real comparisons once again. A freshly charged battery may be warmer than a discharged one. The extra thermal energy also contributes to mass. If you weighed the battery immediately after charging, some of the mass difference could come from heat, rather than the electrochemical energy you actually wanted to compare. To make a clean experiment, you would need to let the charged and discharged battery reach exactly the same temperature while ensuring that no material had entered or left. You would also need to control humidity, pressure, vibration, electrical forces, magnetic effects, and the mechanical influence of any cables or supports. The measurement becomes even more awkward because batteries can change slightly as they charge. Electrode materials may expand and contract. Gas can form in damaged or aging cells. The casing can respond to temperature and internal pressure. Small amounts of material can interact with the environment depending on how the battery is constructed. All of these real-world effects can produce mass or force changes far larger than the pure increase associated with stored energy. So while the theoretical difference is straightforward, designing an experiment that isolates it is not. There is a charming mismatch here between the simplicity of the question and the difficulty of the measurement. Ask whether a full battery weighs more than an empty one, and physics gives a clear yes. Ask someone to place a battery on a scale and demonstrate it directly, and suddenly you need an experimental setup capable of noticing changes smaller than ordinary dust, while keeping nearly every environmental condition under control. The number also helps correct another common explanation. If charging worked by simply adding extra electrons, one might expect the mass increase to be connected mainly to the rest mass of those additional electrons. But a normal battery does not acquire a huge net collection of electrons. The actual relativistic increase follows the stored energy of the complete battery. This is why the effect remains even in an ideal sealed battery, where no net matter crosses the boundary during charging. Suppose we had a magical charger capable of transferring energy into a battery without moving any material across its boundary at all. The battery starts discharged, receives energy, and finishes charged. The number of protons, neutrons, electrons, and atoms inside remains exactly the same. The mass still increases. The few nanograms or micrograms we have been discussing come from the higher total energy of the charged state. That is the part worth holding on to, because it changes what the number means. We are not measuring a tiny pile of new matter that arrived through the charging cable. We are measuring the mass difference between two energetic arrangements of essentially the same material. The charge configuration weighs more because it contains more energy. If you imagine the process in reverse, the picture becomes even clearer. Take the fully charged phone and allow it to run until the battery is discharged. The screen gives off light. The speaker sends vibrations into the air. Radio signals leave the antennas. The electronics warm the phone and the surrounding environment. Energy that once belonged to the battery's internal electrochemical state has spread outward in many forms. After the phone eventually cools back to its original temperature, the remaining device has slightly less mass than it did while fully charged. The missing fraction of a nanogram has not been destroyed. Its equivalent energy has simply left the phone. Some travelled away as electromagnetic radiation. Much of it became heat in the surrounding room. If you expanded the boundary of your system to include the entire room and prevented energy from escaping, the total mass of that larger closed system would remain unchanged. The phone would lose mass while the surroundings gain the energy. This is why physicists care so much about defining the system they are discussing. A battery by itself can gain or lose mass when energy crosses its boundary. A larger closed system containing the battery, charger, wires and everything receiving the waste heat can keep the same total mass even while energy moves from place to place internally. Whether an individual object becomes heavier depends on whether energy has entered it and remained there. There is something almost comical about how precisely nature keeps this account. Your phone does not care that 0.6 of a nanogram is too small for you to notice. The mass still changes. An electric car does not round its few micrograms down to 0 for convenience. Physics keeps the full total even when our instruments and senses cannot. That tiny number also prepares us for one final misconception that appears almost every time this subject comes up. If electricity involves electrons and electrons have mass, perhaps the easiest explanation is still that charging somehow pushes more electrons into the battery. It sounds so natural that it can survive even after we have discussed the chemistry. But the moment we look carefully at electrical neutrality, ion movement, and what the charger actually transfers, that explanation begins to fall apart. The extra weight is real, but it is not simply the weight of a crowd of new electrons arriving through the cable. Understanding why takes us back inside the circuit and forces us to separate electric charge from energy, two ideas that travel together so often that they are very easy to confuse. The idea that charging a battery simply adds more electrons is extremely tempting, and it is easy to understand why. Electricity is associated with electrons. A charger sends an electric current through a cable. Electrons move through that cable. The battery ends up with more stored energy than it had before. Put those facts together quickly and a very natural picture appears. Perhaps the charger is pumping electrons into the battery until it becomes full, rather like a tap filling a bottle with water. If electrons have mass, then perhaps those extra electrons are also the reason the charged battery weighs more. It is a neat explanation, simple enough to fit into a single sentence, and unfortunately it gives us the wrong picture of what a rechargeable battery is doing. To see the problem, imagine what would happen if a charger really did spend several hours pushing electrons into a battery without anything else balancing them. Every electron carries negative electric charge. If the battery continually accumulated more and more electrons, it would become increasingly negatively charged. Those electrons repel one another, so adding each new electron would become more difficult as the charge built up. The battery would also begin producing strong electrical effects around itself. Touching it could produce discharges. Nearby objects could respond to its electric field. Long before the battery reached anything resembling its normal full state, the growing charge imbalance would become the main feature of the device. That is clearly not what happens when you charge your phone overnight. In the morning, the phone does not leap away from your hand because it has become an electrically furious collection of excess electrons. It is still, overall, almost electrically neutral. Electrical neutrality is one of the most important clues in this story. Ordinary matter contains both positive and negative electric charges. Protons in atomic nuclei carry positive charge, while electrons carry negative charge. In an electrically neutral object, these charges balance almost perfectly. There can be tiny local differences and temporary redistributions, especially in electrical circuits. But a normal battery does not become heavily negatively charged simply because it has been charged in the everyday battery sense. The word charged is doing two different jobs here, which is partly responsible for the confusion. An electrically charged object has a net imbalance between positive and negative charge. A charged battery, by contrast, has been placed into an energetic electrochemical state from which it can later supply electrical energy. Those are related ideas, but they are not the same thing. A balloon rubbed against your hair can become electrically charged, because electrons are transferred between materials. The balloon may end up with a small excess of electrons, leaving it with a net negative charge. That charge can make the balloon stick to a wall or attract bits of paper. A rechargeable battery at full charge is different. It has not simply accumulated a large excess of negative charge on the device as a whole. Its internal chemical state has changed while positive and negative charges remain balanced to an extremely high degree. When you connect a charger to a lithium-ion battery, electrons do indeed move through the external circuit. At the same time, positively charged lithium ions move through the inside of the battery. These processes are coordinated. The electron movement is accompanied by changes in where ions are located and how the electrode materials are chemically arranged. The charger is therefore reorganizing charge, rather than simply dumping one type of charge into a container. It may help to imagine a hotel with guests moving between two wings. Suppose a group of people moves from the east wing to the west wing through an internal corridor, while their luggage is transported along a separate route around the outside of the building. At the end of the process, one wing contains both the guests and the corresponding luggage in a new arrangement. The hotel has not gained a huge number of new guests. The same occupants have been reorganized. A battery is obviously doing something rather more sophisticated than moving holidaymakers and suitcases, but the separation of routes is useful. Lithium ions move through the battery internally, while electrons travel through the external electrical path. The final charge state is created by their coordinated rearrangement. This is why following a single electron through the charging process can be misleading. An electron enters one part of the battery through a terminal, but elsewhere another electron may be involved in corresponding changes. The complete electrical circuit remains part of a much larger rearrangement. We should not picture the battery as a warehouse, where every electron entering the charging cable is given a numbered shelf and stored until Tuesday. Electrons are abundant throughout the battery materials already. What matters is their distribution, their available energy states, and their relationship with the ions and atoms making up the electrodes. There is also an enormous number of electrons in an ordinary battery before charging even begins. Every atom contains electrons. The metal current collectors contain electrons capable of moving through the conducting material. The electrode materials contain vast numbers of electrons involved in their chemical and electrical properties. Against that background, the battery does not need to create its useful stored energy by dramatically increasing the total number of electrons inside. The important change is in what those electrons and ions are doing, and in the state the complete collection occupies. Suppose you had two identical sealed rechargeable batteries, one discharged and one charged. If you could perform perfect bookkeeping of every proton, neutron, electron and atom in each battery, the difference in the total number of particles would not be the fundamental reason one weighs more. In the ideal case, you could imagine charging a battery without allowing any net matter to enter at all. Energy would cross the boundary, the internal configuration would change, and the mass would still increase. This thought experiment immediately tells us that extra particles cannot be essential to the effect. The distinction becomes clearer if we separate electric charge from electrical energy. Charge is a property carried by particles such as electrons and protons. Energy describes the state of a physical system and its capacity to produce change. An electron always carries the same amount of electric charge, yet an electron can participate in situations with very different amounts of energy, depending on its motion, its environment, and the fields and materials around it. Knowing how many electrons are present, therefore, does not tell you how much energy a battery stores. Imagine a ball sitting on the floor and the same ball sitting on a high shelf. The number of balls is the same. The mass of the ordinary ball itself is essentially the same for everyday purposes, but the ball and Earth system has more stored gravitational energy when the ball is higher. If we included that energy with perfect relativistic precision, the complete system would have slightly greater mass in the higher energy arrangement. We did not need to add another ball. We only changed the state of the existing one relative to its surroundings. A battery follows the same broad logic. Charging changes the energy associated with the arrangement of matter and charge already present. That increased energy contributes to the mass of the system. Counting particles alone misses the difference, because two systems containing the same collection of particles can have different total energies. This is not unusual in physics. Imagine a box containing gas. Keep the number of gas molecules exactly fixed, but heat the box. The molecules now have more internal energy, and the complete box has slightly more mass. No extra molecules are required. Cool it and let the heat escape, and the mass decreases. Or take a spring and compress it inside a sealed container. The compressed arrangement stores more energy, so the complete container has slightly greater mass, even though it contains exactly the same number of electrons, protons and neutrons as before. The battery is another member of this family. There is an interesting twist here because electrons themselves do have mass. This means that if you genuinely added extra electrons to an isolated object and somehow kept them there, their presence would contribute to the mass of the object. That statement is perfectly true. It simply is not the main explanation for the difference between an ordinarily charged and discharged rechargeable battery. The amount of net electric charge that an everyday object can acquire is also very different from the amount of charge that moves through a circuit during battery operation. This distinction can sound strange at first. A large quantity of electric charge can pass through a wire over time without the wire permanently collecting that charge. Think about water flowing through a pipe. Many litres can pass a particular point during an hour even though the pipe itself does not end the hour containing all those litres. Electrical current similarly describes charge moving through a circuit, not necessarily charge accumulating permanently at one location. When a battery powers a device, electrons move through the external circuit. The same circuit can carry a considerable amount of charge during hours of operation, yet the battery does not simply lose all its electrons. If it did, the result would be spectacularly impractical. Instead, chemical reactions within the battery maintain the process while ions move internally and electrons move externally. The battery approaches a different chemical state as it discharges, but overall electrical neutrality is maintained. Charging reverses that electrochemical movement. The external power source pushes electrons in the required direction through the circuit, while the corresponding ions relocate inside the cell. The energy supplied by the charger is used to move the system away from its discharged equilibrium and toward the higher energy charged arrangement. This is the energy we care about when discussing the increase in mass. There's another reason the extra electron explanation can produce confusion. Suppose we try to estimate the added weight of a battery by taking the amount of electric charge that passes through the charging cable and treating all the corresponding electrons as newly added particles. We would get a completely misleading result because those electrons are part of a circuit. Charge passing through a particular point does not mean an equal amount of net charge remains piled inside the final battery. The process is a circulation and redistribution of charge coupled to chemistry. Your household electrical system offers an even simpler example. When you switch on a lamp, electrons move in the wires. The power station has not been mailing fresh electrons to your home every evening and waiting for you to store them in lamps. The wires already contain an enormous population of mobile charge carriers. The electrical source establishes conditions that make those charges move and transfers energy through the electrical system. The energy delivered to your lamp is not explained by counting newly manufactured electrons arriving from somewhere distant. Something similar happens during battery charging. The charger transfers energy by means of an electrical circuit, and electrons are essential participants in that process, but the electrons are not identical to the energy. This distinction is one of the most useful ideas in understanding electricity. Charge can move while energy is transferred, but energy and charge are not interchangeable words. If that feels slightly odd, think of workers carrying boxes through a warehouse. The workers enable the transport, but they are not the contents of the boxes. The same workers may repeatedly carry different loads without themselves being consumed. In an electrical system, the analogy is imperfect, as all analogies eventually become if kept awake long enough, but it reminds us not to confuse the thing that carries a property with the property being transferred through the complete system. We also have to remember the role of electromagnetic fields. Energy in an electrical circuit is not best pictured as being locked entirely inside individual moving electrons. The arrangement of electric and magnetic fields around the conductors is part of how electrical energy moves from source to load. When you connect a battery to a device, the electrical conditions throughout the circuit change rapidly. Electrons in the wires respond locally, while energy is transferred through the electromagnetic system. This is why a device can begin responding almost immediately, even though the slow average drift of individual electrons through metal would not allow one particular electron to race from the battery all the way to the device at anything close to the speed we associate with the electrical response. The battery itself maintains those electrical conditions because of its internal chemistry. The chemical difference between its electrodes helps create the electrical potential that drives the circuit. During charging, the charger works against that tendency and rebuilds the higher energy chemical arrangement. The electrons are therefore part of a larger system involving chemical forces, electric fields, ions, and electrode structures. This also answers a question that may have been quietly sitting in the background. If the extra mass is not mostly the mass of new electrons, then what exactly becomes more massive? The answer is the battery as a complete system. Its charged state has more total energy, so its total mass is greater. There is no requirement to point at one particular particle and assign the entire increase to it. The mass belongs to the combined system and reflects the total energy of that system. This concept appears throughout modern physics. The mass of a complex object is not always just the arithmetic total of the rest masses of imaginary isolated components. Internal energy matters, binding energy matters, motion inside the system can matter, fields matter. A collection of interacting particles can have a total mass that differs from what you might expect if you considered each particle entirely separately. Atomic nuclei provide a dramatic example. Protons and neutrons bind together inside a nucleus. When a stable nucleus forms, energy can be released. Because energy has left, the mass of the bound nucleus is smaller than the combined mass of those particles when considered separately. Nobody needs to remove a proton to explain the difference. The energy of the arrangement changed. A charged battery gives us the opposite direction of the same bookkeeping. Energy is supplied to create a higher energy arrangement. The resulting system has greater mass. Discharge allows some of that energy to leave, and the mass decreases. Once again, particles do not need to vanish or appear for the system mass to change. This is also why the battery example is a useful antidote to the idea that mass is simply a count of particles. Imagine two completely identical sets of particles arranged into two different systems. One configuration contains more internal energy than the other. The two complete systems can have different masses even though the inventory of particles is identical. Arrangement is not just decoration. In physics, the energy associated with that arrangement contributes to what the system weighs. There is another small complication worth mentioning. In real batteries, tiny amounts of matter can sometimes move in ways that make actual measurements less clean than the ideal picture. Batteries can interact thermally with the environment. Some designs may experience minute gas production or changes due to aging and side reactions. Moisture and contamination can affect a physical sample. These effects could change measured mass for ordinary chemical reasons, but none of them is required for the fundamental result. Even a perfectly sealed ideal rechargeable battery gains mass when energy is stored. The same distinction helps explain why charging from different sources does not change the principle. Charge your battery from a wall outlet, a solar panel, another battery, or a hand-driven generator, and the final increase in mass depends on the energy retained in the battery. These sources may move electrons differently through the external circuit, but if the battery reaches the same internal state, the stored energy and corresponding mass increase are the same. Suppose you charged one phone using electricity from a solar panel and an identical phone using electricity from a power station. If both batteries ended with the same stored energy, there would be no special solar mass and no power station mass hiding inside them. Energy does not retain a little label explaining where it came from. Once transferred into the battery's internal state, it contributes to the energy and mass of that system. The electron misunderstanding can also arise because we sometimes describe a battery by how much electric charge it can deliver. Battery specifications often include a measure related to the amount of charge that can move through a circuit during discharge. That is useful for engineers and consumers, but it does not mean the battery contains that many extra electrons when full. It describes how much charge can be transferred through the external circuit as the battery moves between its chemical states. Imagine a revolving door at the entrance to a building. During the day, thousands of people may pass through it, even though the building never contains thousands of additional people all at once. Counting passage through the door tells you something about traffic, not the final population inside. In much the same way, counting electric charge moving through a circuit tells us about the electrical process without implying that the same charge permanently accumulates inside the battery. This is why a battery can repeatedly charge and discharge without requiring a fresh shipment of electrons in the ordinary material sense. The system is cycling between chemical arrangements. Energy enters during one direction and leaves during the other. Charge moves as part of that process, but the device remains approximately neutral throughout. There is a nice consequence of this distinction when we return to the question of weight. If the extra mass was simply caused by extra electrons, we might expect a charged battery to become noticeably electrically negative as its mass increased. But no such connection is required. A perfectly neutral system can become more massive by storing energy. Heat a neutral box and its mass increases. Compress a neutral spring and its mass increases. Charge a neutral battery electrochemically and its mass increases. None of these examples requires the object to develop a large net electric charge. Even light can increase the mass of a closed system without adding electric charge at all. Trap radiation inside a perfectly reflecting box, and the energy of that radiation contributes to the total mass of the box. Release it, and the box loses energy and becomes slightly less massive. The box could remain electrically neutral throughout. Once we see this, the idea that mass increase requires additional charged particles becomes much less convincing. The full battery is therefore heavier for a deeper reason. The charger has transferred energy into the battery and changed the state of the complete system. Electrons helped make that transfer possible. Ions moved as part of the internal chemistry. Electric fields played their role. Chemical interactions were rearranged. But the tiny increase in mass belongs to the higher energy state as a whole. This also gives us a cleaner picture of what happens as the battery discharges. Electrons move through the external circuit, but we should not imagine the battery becoming lighter, because individual electrons are being permanently thrown away into the phone. They circulate through the connected electrical system, while the battery chemistry changes. The mass decreases because usable internal energy is transferred out of the battery. Much of that energy eventually becomes heat in the phone and its surroundings, while some leaves as light, sound, and electromagnetic radiation. If the phone, battery, emitted light, surrounding air, and every other recipient of that energy was somehow enclosed inside one perfectly sealed box, the total mass of the entire box would remain constant. The battery inside would lose stored chemical energy, but that energy would remain elsewhere in the box as heat, light, motion, and other forms. Only the distribution would change. Open the box and allow energy to escape, and the mass of what remains inside would decrease. That is the accounting Einstein's physics asks us to follow. Do not only count particles, follow the energy as well. Once we do that, the charged battery stops looking like a container swollen with additional electrons. It becomes something more interesting. It is nearly the same collection of matter arranged in a state with more internal energy. The electrons are essential to how that state is created, and how its energy is later transferred, but they are not a hidden cargo whose ordinary particle mass explains the difference on the scale, and that leaves us with a practical problem that is almost more entertaining than the misconception itself. If the true difference between a charged and discharged battery can be smaller than ordinary dust, smaller than tiny changes in moisture, and easily overwhelmed by temperature and air movement, could anyone actually weigh it? In principle, the physics says the difference is there. Turning that clean statement into a real experiment is another matter, because the moment we try to place such a battery on an actual balance, the quiet laboratory around it suddenly becomes full of effects, far larger than the one we're trying to find. A laboratory version of this question sounds almost embarrassingly simple. Take a battery, weigh it while it is discharged, charge it, weigh it again. If the second measurement is larger, then there is your answer. Unfortunately, the moment you try to perform that experiment seriously, the ordinary world begins interfering with almost comic enthusiasm. The change in mass caused by the stored energy is so small that effects we normally ignore become enormous by comparison. Temperature matters, air movement matters, humidity matters, dust matters. The way the battery is sitting on the balance matters. Even a cable touching the setup can produce a force many times larger than the difference you are trying to detect. Physics gives us a very clear prediction, but nature does not promise that the easiest experiment will also be the cleanest one. Imagine beginning with a small rechargeable battery on an extremely sensitive balance. The battery has been allowed to sit for a long time so that its temperature matches the room. You record its mass, then you charge it and return it to the same balance. Immediately there is a problem. Batteries tend to warm during charging. Even if the increase is only slight, a warm battery changes the air around it. Air touching the surface warms, becomes less dense, and begins to move. Those tiny air currents can push on the balance or change the apparent weight of the object. On an ordinary scale, this means nothing. On a balance sensitive enough to search for a few nanograms, it can completely bury the effect. You might solve that by waiting until the battery cools back to exactly the same temperature as before. That helps, but now another problem appears. The battery has been sitting in air for a different amount of time. Its surface may have absorbed or released a microscopic amount of moisture. Some materials attract thin layers of water molecules from the atmosphere. The amount involved can be invisible and still exceed the mass difference caused by charging. A fingerprint becomes a serious experimental event. A small piece of dust becomes an unwelcome visitor with a mass budget far larger than the relativistic effect you're hoping to see. The obvious solution is to perform the experiment in a vacuum, where there is no air movement and much less trouble from atmospheric moisture. That removes several problems at once, but it introduces others. Batteries are chemical devices, and placing them in unusual environmental conditions can affect temperature control, heat removal, pressure, and sometimes the battery itself. You would also need a way to charge the battery while it remained inside the experimental chamber. Any wires connected to it could tug on the measuring apparatus. Electrical currents in those wires could create magnetic forces. Electric fields could interact with surrounding surfaces. The cable might expand slightly as it warmed. At the scale we are discussing, a wire does not have to pull very hard to ruin your afternoon. Perhaps you could disconnect the battery after charging and then weigh it. That eliminates the cable force during the measurement, but now the battery has to be moved or mechanically disconnected without changing anything else. Touching it may transfer heat, a connector may move, the battery may shift position by a tiny amount. If the balance responds differently depending on exactly where the object sits, that becomes another source of error. A measurement that began as charge the battery and weigh it again has become a careful exercise in preventing almost everything in the room from doing anything interesting. There is also the battery itself to consider. Real batteries are not perfectly reversible objects that move between two states without any side effects. Charging and discharging can produce small changes in volume. Electrode materials expand and contract as ions move in and out of their structures. Internal pressure can change. A battery may warm unevenly. Very small side reactions can occur. An aging cell can produce gases or permanently alter some of its internal material. None of these effects changes the basic fact that stored energy contributes to mass, but they make a direct experimental comparison more complicated. Suppose the battery casing expands slightly during charging. Its actual mass may have increased only by the tiny amount associated with stored energy, but its larger volume displaces slightly more air when weighed in the atmosphere. That changes the buoyant force acting on it. We usually associate buoyancy with boats and balloons, but every object weighed in air experiences a small upward force because it displaces air. For kitchen scales, we can safely ignore this. For extremely precise mass measurements, we cannot. A tiny change in battery volume can change the apparent reading by more than the effect we are looking for. This is one of the reasons high-precision weighing often becomes less like putting something on a scale and more like managing an entire environment. Temperature and pressure must be monitored. Air density must be known. Vibrations must be reduced. Electrostatic charge must be controlled. The instrument itself must be stable. The sample must be clean. Measurements may need to be repeated many times so that random fluctuations can be separated from a consistent effect. The laboratory table may be isolated from the floor because footsteps matter. Nearby equipment may need to be turned off because vibration matters. At some point, the battery has become the quietest participant in the experiment. Gravity itself is not perfectly constant from moment to moment at the level demanded by the most sensitive measurements. The gravitational influence of the moon and sun produces tiny changes known as earth tides. The solid ground beneath a laboratory rises and falls slightly over time. Atmospheric pressure changes redistribute mass above the measurement site. Groundwater can move. Nearby people and objects exert their own tiny gravitational pulls. None of these things makes your bathroom scale suddenly unreliable, but precision measurement eventually reaches a point where the environment stops being background scenery and becomes part of the experiment. Even the person operating the equipment is a gravitational object. Stand close enough to an extremely sensitive apparatus, and your body exerts a tiny attraction on it. You do not need to worry about accidentally pulling your phone across the bedside table through gravity alone, but precision physics has a habit of making ordinary human presence inconvenient. Researchers sometimes design measurements so that the operator can remain farther away, not because scientists are naturally antisocial, but because several dozen kilograms of moving human being can be an unnecessary complication when the effect of interest is extraordinarily small. Then there is electrical charge in the ordinary static sense. Although the battery remains nearly neutral overall, surfaces and insulating materials can acquire small static charges during handling. Those charges can create electrostatic forces between the battery, balance, chamber, cables, and surrounding structures. A static force that would be completely irrelevant anywhere else can imitate a change in weight. If you rubbed a plastic object against fabric and placed it near a very sensitive balance, the electrical attraction could easily overwhelm the mass effect associated with charging a battery. The experiment therefore has to control not only how much energy the battery contains, but also where stray electrical charges have ended up. Magnetic effects present another nuisance. Batteries contain conducting materials, and charging involves electric current. Current produces magnetic fields. Some battery components may respond weakly to magnetic fields in the environment. Nearby equipment, motors, transformers, speakers, electrical wiring, and even the measurement instrument itself can contribute magnetic influences. Once again, these forces do not challenge the underlying physics. They simply make it harder to say that a tiny change in the balance reading came from mass, rather than from some other interaction. One possible strategy would be to avoid comparing two separate batteries entirely. Instead, use the same battery and repeatedly move it between charged and discharged states, while performing many measurements. If the apparent mass consistently rises after energy is stored and falls after the same energy is removed, that repeated pattern could help distinguish the real effect from random drift. The difficulty is that cycling the battery also changes its condition over time. Batteries age, capacity changes, internal resistance changes, the amount of energy lost as heat can vary. A perfectly repetitive experiment requires a battery that is more perfectly repetitive than real battery chemistry usually allows. Another approach would be to choose an energy storage system that behaves more cleanly than a chemical battery. A capacitor, for example, can store electrical energy without relying on the same kind of complicated electrochemical reactions found in a battery. Charging a capacitor separates electrical charge and stores energy in the electrical configuration of the system. In principle, a charged capacitor also has more mass than the same capacitor when discharged. Because the process can be made highly controlled, such a system may be conceptually cleaner for demonstrating the underlying relationship between stored energy and mass. A mechanical system offers another possibility. A flywheel can store energy by spinning. If you could place a rapidly rotating flywheel inside a perfectly sealed apparatus and compare it with the same flywheel at rest, the spinning system would have slightly greater mass because it contains more energy. A compressed spring can do the same thing. Heat can do it. Trapped light can do it. These examples remind us that the battery is not special in the rule it follows. It is only one particularly familiar way of storing energy. If your goal were simply to confirm that energy contributes to mass, you would therefore not necessarily choose a phone battery as the easiest experimental object. The chemistry introduces too many small complications. A physicist would usually prefer a system where the amount of added energy can be controlled very precisely, and where changes in temperature, material distribution, pressure, and chemical composition can be reduced or measured independently. There is an important distinction here between direct measurement and indirect confirmation. We do not need to place a phone battery on a balance and personally watch the final digit move before we can be confident that its mass changes. The relationship between energy and mass has been tested across many areas of physics with extraordinary precision. Nuclear reactions, particle physics, atomic physics, and other experiments repeatedly show that changes in a system's energy correspond to changes in its mass. Once that relationship is established, applying it to a battery does not require a new law. We determine how much additional energy the charged state contains, and that tells us the associated increase in mass. In that sense, the battery question is a little like asking whether someone standing on a mountain experiences a slightly different gravitational environment from someone at sea level. You may not personally feel the difference, but the theory connecting height and gravity has been tested independently and can predict what happens. The inability of your senses to detect the effect is not a serious objection. Human senses were designed by evolution to keep us alive at useful everyday scales, not to function as nanogram balances or precision gravitational instruments. Still, imagining the direct experiment is valuable because it teaches us how careful measurement works. A scientific instrument does not automatically tell us the thing we want to know. It produces a reading influenced by many physical processes at once. The experimenter's job is to understand those processes well enough to separate the desired effect from everything else. Suppose a balance tells you that the charged battery appears slightly heavier. That alone would not be enough. Perhaps the battery is warmer and the scale responds to temperature. Perhaps moisture collected on its surface. Perhaps its volume changed and altered air buoyancy. Perhaps an electrostatic attraction increased. Perhaps the balance drifted between measurements. A convincing experiment has to rule out those alternatives or show that they are much smaller than the claimed effect. Now suppose the charge battery appears slightly lighter. That would not immediately disprove the relationship between energy and mass either. The battery may have lost a tiny amount of material during charging. Warm air could produce an apparent upward force. A surface contaminant could have evaporated. Something mechanical could have shifted. Measurements only become meaningful when we understand what the instrument is actually responding to. This is why experimental physics can look surprisingly cautious from the outside. Researchers repeat measurements, reverse procedures, calibrate instruments, compare reference objects, vary conditions, and deliberately search for ways the experiment might be misleading them. The most interesting question is often not whether the number moved, but whether anything else could have moved it. For our battery, one especially useful technique would be to compare the energy transferred during charging with the expected mass change rather than relying only on a single before and after measurement. If the battery receives a known amount of stored energy, the theory predicts a corresponding increase in mass. Repeating the process at different amounts of stored energy would give a stronger test. A battery charged only part of the way should show a smaller increase than the same battery charged more fully, assuming all other conditions could be kept equal. The pattern matters as much as any single reading. In practice, however, measuring the precise energy retained by a chemical battery has its own complications. Not all energy entering through the charger remains stored. Some becomes heat. The amount lost depends on current, temperature, battery condition, and other factors. You would therefore need to measure the energy entering the system and also account for energy leaving as heat during the process. Once the battery returned to its starting temperature, you could estimate how much additional electrochemical energy remained inside. There is a wonderfully inconvenient feature of this experiment. To detect the relativistic mass increase cleanly, you want the battery to be at exactly the same temperature before and after charging. But while waiting for it to cool, the battery may slowly self-discharge. That means some of the stored energy you hope to weigh is already escaping. You then need a battery with very low self-discharge, excellent thermal control, and enough patience to allow everything to settle without allowing the state you are measuring to change significantly. Physics does occasionally behave as though it has read the experimental plan and decided to add a few extra conditions. A larger battery might seem to solve the problem because it stores more energy and therefore gains more mass. That does help in one sense. An electric vehicle battery stores vastly more energy than a phone battery, so the relativistic increase is much larger. Unfortunately, the battery pack is also enormous, complicated, thermally active, mechanically complex, and difficult to place on an instrument sensitive to a few micrograms. Cooling systems move fluids. Structural components change temperature. The pack may expand. Electrical systems produce fields. Measuring a tiny mass change in a very large object can be harder than measuring an even smaller change in a carefully designed laboratory sample. We could instead store a much larger amount of energy in a specially designed experimental system where the background effects are controlled. The more energy stored, the larger the corresponding mass difference becomes. At some point, the effect becomes easier to detect, but increasing stored energy often introduces new engineering problems. More heat may be produced, stronger fields may be required, mechanical stresses may increase, safety becomes more important. There is no magical point where nature stops demanding careful accounting. This teaches us something important about the difference between a principle being measurable and a measurement being convenient. The mass increase of a charged battery is measurable in principle because it is a real physical quantity. With sufficiently sensitive instrumentation and sufficiently good control of environmental effects, there is nothing fundamentally preventing us from detecting it. But a casual demonstration with an ordinary battery is not realistic, because the signal is so small compared with the noise. That phase signal compared with noise appears throughout experimental science. The signal is the effect you care about. The noise is everything else changing the measurement. Improving an experiment often means making the signal larger, making the noise smaller, or repeating the measurement until a consistent pattern emerges from random fluctuations. For the battery, the signal may be a few nanograms or micrograms. The noise comes from heat, air, moisture, mechanical forces, electrical effects, chemistry, and instrument drift. It is a rather crowded competition. There is another way to appreciate the problem. Imagine trying to measure the mass gained by a phone battery, while someone places and removes tiny specks of dust from the phone at random. The dust particles are much heavier than the effect you want. Even if your scale were sensitive enough, the reading would jump around for reasons unrelated to the stored energy. Real experimental disturbances are more subtle than visible dust, but the principle is the same. Sensitivity alone is not enough. You also need control. This is why an extraordinarily precise scale placed in an ordinary room does not automatically become an extraordinarily precise experiment. The more sensitive the instrument becomes, the more of the world it notices. Air conditioning that seemed gentle becomes a changing force. A nearby door closing becomes a vibration. Temperature differences across the room become important. Static electricity becomes troublesome. The floor becomes less solid than you imagined. Even time of day can correlate with temperature, traffic, human activity, and other environmental changes. At a certain level of precision, measuring one tiny thing means learning far more about everything around it than you ever expected. That is one of the quiet pleasures of experimental physics. The universe does not present phenomena in separate labelled boxes. Gravity, heat, electricity, mechanics, chemistry, and the atmosphere all arrive together. The experiment works only when you learn how to untangle them. For our purposes, though, we do not need to build that laboratory. The important result is already clear. A battery storing more energy has more mass, and the size of that increase follows directly from the amount of energy stored. The reason we do not weigh it easily is not that the additional mass is somehow unreal. It is that everyday energy storage changes mass by an amount fantastically smaller than the ordinary material changes and environmental forces surrounding the object. Once you start looking at the problem this way, the battery stops being an isolated curiosity. The same hidden increase appears whenever we put energy into a system and keep that energy there. A hot object is heavier than the same object after it cools. A compressed spring is heavier than the same spring after it relaxes and releases its energy. A spinning object contains more energy than the same object at rest, and therefore contributes more mass to the complete system. A container holding trapped radiation is heavier than the same container after that radiation escapes. The numbers may be tiny, but the rule follows us everywhere. Even your own surroundings are full of objects whose masses are shifting by unimaginably small amounts as energy moves through them. A laptop warms and cools, a phone charges and discharges. Food is chemically transformed. Light enters a room and is absorbed by surfaces. A kettle heats water. A refrigerator transfers heat. A spring in a mechanical device is compressed and released. None of these changes makes the furniture noticeably heavier or lighter, yet the accounting of mass and energy never stops. The battery gave us a convenient place to begin because its percentage indicator makes stored energy feel visible. We can watch the number rise and know that energy is accumulating in the electrochemical state. But once we understand why that increases mass, the same idea begins appearing in places with no battery icon at all. Energy has been contributing quietly to the mass of ordinary objects the entire time, whether we were watching a screen tell us that something was full or not. Once you notice that stored energy contributes to mass, the idea refuses to stay inside the battery. The phone beside you may have been the easiest place to begin because its battery percentage gives us a convenient way to watch energy being stored and released. But the same principle is operating in objects all around you. Most of the time, the changes are so small that they pass completely unnoticed. A cup cools on a table and loses a tiny amount of mass as thermal energy leaves it. A spring is compressed and gains a tiny amount of mass because energy has been stored in its arrangement. A spinning wheel contains more energy than the same wheel at rest, and therefore contributes slightly more mass to the complete system. None of these changes will trouble your furniture or require you to adjust a set of scales, but they all belong to the same physical accounting that makes a charged battery heavier than a discharged one. Consider something as ordinary as a cup of tea. When the tea is freshly made, the water contains more thermal energy than it will after sitting in the room for an hour. The molecules are moving and interacting with more energy. If the cup, tea, and everything contained within them could be weighed with perfect precision, while preventing evaporation or any other material from escaping, the hot cup would have slightly more mass than the same cup after it cooled and released heat into the surroundings. As the thermal energy moves into the air, table, and nearby objects, the mass associated with that energy moves with it. The cup becomes lighter by an amount far too small for any kitchen scale to notice, while the environment receiving the energy becomes correspondingly more massive. This does not mean that heat is made from tiny heavy particles that pile up inside hot objects. It means that the increased internal energy of the material contributes to the total mass of the system. The molecules in the hot tea move differently from those in the cooler tea. Their microscopic state contains more energy. When that energy leaves, the mass of the tea decreases slightly. The number of water molecules can remain exactly the same throughout the comparison. Once again, the arrangement and motion of the existing matter are enough to change the total mass. A compressed spring gives us the same result in a different form. Imagine placing a spring inside a sealed box and weighing the box while the spring is relaxed. A mechanism inside the box then compresses the spring and locks it in place without adding any material from outside. The spring now contains stored elastic energy. The box has become slightly more massive. Release the spring and allow its motion to become heat through friction. If all that heat remains trapped inside the sealed box, the total mass does not fall because the energy has not left. It has only changed form. Allow the box to cool by releasing that heat into the room, and its mass decreases. The important question is not whether the energy is chemical, mechanical, electrical, or thermal. The important question is whether the energy remains inside the system we are considering. A wound mechanical watch works in much the same way. When you wind the spring, your muscles provide energy. The internal mechanism stores some of it. The fully wound watch therefore has slightly more mass than the same watch after it has run down and released that energy. As the watch operates, the stored energy becomes motion in the gears, tiny amounts of sound, and mostly heat. Eventually that energy reaches the surrounding environment. The watch becomes lighter, although the change is so small that losing a microscopic speck of dust from the case would be a far more important event for any practical measurement. The same principle applies to a clock with a raised weight. Some older clocks store energy by lifting a mass higher against gravity. When the mass is raised, the complete system containing the clock and earth has more stored gravitational energy. As the weight slowly descends and powers the mechanism, that energy is transferred away. From the viewpoint of relativity, the energetic state and mass of the full system are connected even though nothing has been added to the weight itself. Food provides another familiar example. A piece of food contains chemical energy that can be released through reactions in your body. The useful energy does not come from additional secret material hiding between the molecules. It is connected to the chemical arrangements within the food and to the reactions those molecules can undergo. As those reactions take place, energy is transferred into motion, electrical activity in cells, the maintenance of body temperature, the construction of molecules, and many other processes. Eventually much of it spreads into the environment as heat. This does not mean that the mass you lose by exercising is simply the direct mass equivalent of the energy you used. Human metabolism involves matter leaving the body as carbon dioxide, water, and other substances, and that ordinary transfer of material accounts for vastly more mass than the tiny relativistic change associated with the released chemical energy. The point is simply that chemical energy itself contributes a small amount to the mass of the system containing it, just as the chemical energy in a battery does. Even a room changes mass as energy moves through it. Switch on a lamp in a perfectly sealed room, and energy enters the lamp electrically. The lamp converts that energy into light and heat. The light travels across the room and is absorbed by walls, furniture, and other surfaces, where it eventually becomes additional thermal energy. If the room were truly sealed so that no energy could escape, the total mass of the room would increase by the mass equivalent of whatever energy had been supplied from outside. Turn off the lamp, and the room would remain slightly more massive until that energy was allowed to leave. In a real room, of course, heat escapes through walls, windows, ventilation, and radiation. Energy is constantly crossing the boundaries of the space. Sunlight enters, warm air leaves. Electrical energy arrives through wires. Light escapes through windows. Appliances transfer heat. People enter carrying chemical energy in their bodies and leave having released some of it into the room. The total mass is changing by tiny amounts all the time, although ordinary changes in air, moisture, dust and people are so much larger that the relativistic contribution is completely hidden. Light itself gives us one of the clearest demonstrations that energy does not need ordinary rest mass in order to affect the mass of a larger system. Imagine a perfectly reflecting box with light trapped inside. The light repeatedly reflects from one wall to another and cannot escape. The box containing that light has more mass than the same empty box. Release the light through an opening and the remaining box loses mass because energy has left. Nothing resembling ordinary matter had to be added for the mass of the system to increase. That example is important because it separates two ideas that are easily mixed together. Individual particles of light do not have rest mass, yet the energy they carry contributes to the mass of a closed system containing them. This is another reason it is safer to think in terms of the total energy of a system, rather than imagining that mass must always come from adding up tiny material objects. A spinning flywheel provides a more mechanical example. A flywheel at rest contains the ordinary energy associated with its matter. Spin it rapidly, and you have added rotational energy. The complete flywheel now has slightly more mass than it did at rest. Slow it down, and allow that energy to leave as electricity or heat, and its mass decreases. Engineers actually use large flywheels as energy storage devices in some applications. Their mass change from stored energy is still extremely small, but the principle is exactly the same as with batteries. Water stored behind a dam gives us another version. Water held at a higher elevation has more gravitational energy than the same water at a lower elevation. When the water flows downhill through turbines, that energy can be converted into electrical energy and sent across the power grid. If we considered the water and earth as a complete physical system, the higher energy arrangement corresponds to slightly more mass than the lower energy arrangement after the energy has escaped elsewhere. This means that when electrical energy is stored by pumping water uphill, the full system gains mass. When the water later flows back down and the energy is sent away through wires, the system loses that tiny contribution. Nobody operating a hydroelectric plant needs to include this change when calculating how much load a dam can support. The amount is too small to matter for engineering purposes. Nature includes it anyway. A similar story applies to energy stored in compressed air. Use a machine to compress gas inside a sealed tank, and the system gains energy. Some of that energy may initially appear as heat, which is why gas is warm when compressed. After the tank returns to its previous temperature while remaining compressed, it still contains energy associated with the pressurized state. The complete system has more mass than it would after the compressed gas is allowed to expand and its energy escapes. None of these examples requires a battery, and that is precisely the point. Batteries are not unusual because energy contributes to their mass. They are unusual only because they offer such a familiar and convenient way of storing useful energy. The same rule applies wherever energy can be placed into a system and retained. There are places where the mass differences become much more significant. Atomic nuclei are held together by powerful interactions. When certain nuclear arrangements change, much larger amounts of energy can be released compared with ordinary chemical reactions. The remaining system then has measurably less mass than the original one because energy has escaped. This is part of the reason nuclear reactions can release so much energy from relatively small amounts of material. The Sun provides a vast example of this process. Deep inside it, nuclear reactions convert lighter atomic nuclei into more tightly bound arrangements. Energy is released and eventually travels outward before leaving the Sun as radiation. Because the Sun continually loses energy into space, it also continually loses the corresponding mass. Some of that energy crosses the enormous distance to Earth and arrives as sunlight. When sunlight reaches the Earth and is absorbed, that energy becomes part of the energy of our planet. It can warm the ground and oceans, drive weather, support photosynthesis, and eventually spread into many other forms before Earth radiates energy back into space. At every stage, mass and energy remain connected. The individual changes are often tiny compared with the mass of the objects involved, but the accounting never stops. Plants give us a particularly familiar route through this process. A plant absorbs light from the Sun and uses some of that incoming energy to help build higher energy chemical arrangements. Later, animals or people can eat material produced by plants and release some of that chemical energy through metabolism. Energy that began as radiation from the Sun can become stored chemical energy on Earth. The systems holding that energy possess slightly more mass than they would without it. A rechargeable battery powered by a solar panel makes the route even easier to follow. Sunlight arrives at the panel. The panel converts part of that energy into electrical energy. The charger uses the electrical energy to rearrange the battery's internal chemistry. The battery becomes slightly more massive because more energy is now stored inside it. Later, the battery powers a lamp. Energy leaves the battery, travels through the circuit, becomes light, and is absorbed by the room. The battery loses its tiny extra mass while the receiving environment gains energy. At no point do we need energy to become a separate substance. We simply follow what happens to the total energy of each system as it changes form and location. There is another everyday example hiding inside devices that do not use batteries at all. A capacitor stores energy by separating electric charge and maintaining an electric field. Charge the capacitor and its mass increases slightly. Discharge it and allow the energy to escape, and the mass decreases. The mechanism differs from battery chemistry, but the result is the same because the total energy has changed. A magnet can participate in similar energy changes depending on how magnetic systems are arranged. Separate objects that attract each other, and you may need to supply energy. Hold them in that configuration, and the system stores more energy than it would in a lower energy arrangement. The mass of the complete system reflects that difference. Release the objects, and the energy may become motion and eventually heat. If the heat remains within a closed system, the total mass stays the same. If it escapes, the mass decreases. By now, a pattern becomes difficult to miss. Energy stored as heat counts. Energy stored chemically counts. Energy stored electrically counts. Energy stored mechanically counts. Energy carried by light counts. The particular mechanism determines how the energy behaves and how useful it may be, but the contribution to the total mass of the system follows the same underlying principle. This can change the way we think about the word mass. In ordinary life, mass seems to be a simple inventory of material. Put more matter into a box and it becomes more massive. Take matter out and it becomes less massive. That remains perfectly useful for almost everything we do. But at a deeper level, the complete mass of a system also reflects the energy contained in its internal state. This is why two systems containing the same kinds and numbers of particles can have slightly different masses. One may be hotter, one may contain a compressed spring, one may contain trapped light, one may be a charged battery. Their material inventory can look essentially identical while their total energies differ. The effect can also work in the direction that initially seems more surprising. A tightly bound system can have less mass than its separated components. If bringing the parts together releases energy, and that energy leaves, the finished system has lost some total energy and therefore has less mass. This is not an exception to the rule. It is the same rule viewed from the other direction. Add energy and retain it, and the mass rises. Release energy and allow it to leave, and the mass falls. Our battery provides a particularly neat cycle because we can repeat the process. Charge it and energy enters. The internal electrochemical arrangement changes and the mass rises. Use it and energy leaves. The battery moves toward its discharge state and the mass falls. Recharge it and the tiny difference returns. If the battery were perfectly reversible and never aged, this could continue indefinitely. Real batteries slowly change, of course. Their materials degrade, side reactions occur, and their capacity declines. But those practical imperfections do not alter the basic relationship between stored energy and mass. There is something useful about remembering how small the effect is. Saying that energy has weight can make it sound as though a charged phone ought to feel different in your hand. It will not. The mass associated with the stored energy is fantastically smaller than the ordinary mass of the device. The statement is interesting because it reveals something fundamental about physics, not because it creates a new household method for checking whether your phone needs charging. If you picked up two otherwise identical phones, one charged and one discharged, any difference you thought you felt would come from something else. Perhaps one phone has a case. Perhaps one has dust in a speaker opening. Perhaps one is warmer. Perhaps you simply expected it to feel different. Human hands are impressive instruments, but detecting fractions of a nanogram is not one of their better features. The same caution applies when someone places a battery on an ordinary digital scale and claims to have measured the effect directly. If the scale changes by a visible amount, something other than the relativistic mass of the stored energy is almost certainly responsible. Temperature, positioning, calibration, moisture, vibration, or ordinary material changes are much more likely. The true effect is far smaller than a household scale can resolve. That does not make the idea any less physical, quite the opposite. One of the useful lessons of modern physics is that reality continues far beyond the range of our senses. We do not feel the small relativistic corrections affecting clocks in satellites, yet navigation systems must account for them. We do not feel the gravitational attraction of a nearby chair, but it is there. We do not notice the mass change when a battery charges, but the underlying connection between energy and mass remains. So the next time you plug in a phone, laptop, camera, or pair of headphones, you can think about what the charging process is actually doing. Energy travels through the charger and into the device. Electrons move through the external circuit. Ions move inside the battery. The internal chemical arrangement is driven into a higher energy state. The battery stores the ability to transfer that energy later, and because the total energy of the system has increased, so has its mass. When you unplug the device and begin using it, the process reverses. The electrochemical state moves toward a lower energy configuration. Energy travels through circuits and becomes computation, light, sound, radio transmission, vibration, and heat. Eventually, most of it spreads into the environment. The battery becomes lighter by the same tiny amount associated with the energy it has lost. What looked at first like a peculiar fact about batteries turns out to be a general property of physical systems. A full battery weighs more not because electricity has been poured into it, as though it were a liquid, and not because the charger has packed it with a large collection of extra electrons. It weighs more because the charged state contains more total energy than the discharged state. That same idea is present in warm objects, compressed springs, spinning wheels, electric fields, chemical fuels, trapped light, atomic nuclei, and countless other systems. The scale of the effect changes enormously, but the principle remains consistent, and there is something fitting about finding such a fundamental piece of physics inside an object we barely notice anymore. A battery can sit silently on a table doing absolutely nothing obvious, while holding energy in a carefully prepared internal state. There is no sound, no visible motion, and no indication from its weight that anything important has changed. Yet compare it with the same battery after that energy has been released, and they are not physically identical. The difference is small enough to hide beneath dust, heat, and fingerprints, but it is still part of the object. Perhaps your own phone has lost a little charge while you have been listening. If it has, then some of the energy that was stored in its battery earlier has already moved elsewhere. A small amount became light from the screen. Some became sound. Some travelled away as radio waves. Much of it became heat in the device and the air around you. Along with that escaping energy went an unimaginably small amount of mass. And if the phone happens to be charging instead, then the opposite is taking place. Somewhere through the cable, energy is arriving, the chemistry inside the battery is being rearranged. The stored energy is increasing, and with it the mass of the device by an amount you will never feel, but which the laws of physics keep track of perfectly well. So a full battery really does weigh more than an empty one. The difference is not a trick of language, and it is not merely a convenient analogy. It is a consequence of the fact that mass belongs not only to the particles we can count, but to the total energy of the physical system they form. Once that connection becomes clear, the little battery icon on a screen starts to represent something slightly more interesting than how long you have until the next charger. It is also showing you, in its own very practical way, a tiny change in the mass of the object in your hand.